If you enjoy slow, thoughtful explorations of the natural world, consider liking the video and subscribing to the channel. It helps this quiet corner of science continue to grow. And before settling in, take a moment to share where you're watching or listening from tonight. A coastal city? A mountain town? Somewhere dry and sunlit? Somewhere wrapped in rain? Wherever that place is, the sky above it is doing something. It may look still. It may look empty. It may seem calm enough to ignore. But even now, air is moving. Heat is rising. Water is changing phase. Invisible rivers of wind are flowing thousands of meters overhead. The atmosphere never truly rests. Weather feels familiar. It taps on windows, cools skin, soaks pavements, rattles leaves. It is so ordinary that it is often overlooked. Yet weather is one of the most intricate physical systems on Earth. It is the constant negotiation between sunlight and gravity, between rotation and water, between order and instability. And all of it happens in a layer of air so thin, on planetary scale, that if Earth were the size of a classroom globe, the atmosphere would be thinner than a coat of varnish. That thinness is part of the mystery. How can something so fragile carry the power of hurricanes? How can air, which feels weightless and invisible, organize itself into spiraling storms the size of continents? Why does it rain in one town while another remains dry just a few kilometers away? And why, despite satellites, radar, and supercomputers, does the sky still surprise us? Weather is not random. It is not chaotic in the way it sometimes appears. It follows physical laws with remarkable consistency. The ideal gas law, the laws of thermodynamics, the conservation of energy, the influence of Earth's rotation described by the Coriolis Effect. These are not abstract textbook ideas. They are active in the clouds above your head. The wind that brushes past a window tonight may have begun as sunlight warming the equator days ago. The rain falling on a rooftop may have carried energy released invisibly when water vapor condensed high in the troposphere. The storm forming over an ocean may be drawing strength from heat stored in water months earlier. Weather is movement. It is energy redistributing itself. It is imbalance seeking equilibrium over and over again. And yet it is also delicate. A slight shift in temperature, a subtle change in humidity, a small disturbance in pressure. These tiny differences can scale upward into thunderstorms, blizzards, or heat waves. The atmosphere amplifies, it organizes, it evolves. There is something quietly humbling in that. Every location shared in the comments is part of the same planetary system. The sky above a desert, a rainforest, a city skyline, or a quiet rural field is connected through global circulation. The air moves in vast looping patterns known as Hadley cells, feral cells and polar cells, linking equator to pole. High above, jet streams ripple like invisible rivers. Below, oceans store and release heat in cycles that shape seasons. Nothing in weather happens in isolation. Even now, as this introduction unfolds, somewhere sunlight is heating dark ocean water. Somewhere warm air is rising. Somewhere cold air is sinking. Somewhere tiny droplets are forming around microscopic particles of dust. Somewhere a low-pressure system is beginning to rotate. The sky is always in motion. Understanding how weather actually works does not require memorizing charts or symbols. It begins with something simpler. It begins with recognizing that the atmosphere is a physical system, governed by pressure, temperature, density, moisture, and motion. It begins with energy. From there, patterns emerge, convection cells form, winds align, water evaporates and condenses, storms organize themselves into spirals, fronts collide, jet streams shift. All of it follows understandable principles. All of it unfolds according to laws that can be described clearly and calmly. And yet, even when explained, weather retains a certain quiet strangeness. Air that cannot be seen carries oceans of water vapor. Heat that cannot be felt high above determines the storms below. A planet turning steadily through space shapes the direction of winds in ways that are subtle, yet powerful. The sky above may look peaceful tonight, but it is not static, it is not passive. It is a dynamic, flowing system powered by the sun and shaped by Earth's rotation. So wherever you are listening from, beneath clear stars, drifting clouds, distant thunder, or steady rain, the same physical story is unfolding overhead. In this slow exploration, the invisible machinery of the atmosphere will gradually come into focus, not dramatically, not urgently, but carefully, because weather is not magic, it is physics, and once its quiet mechanisms are understood, even the simplest breeze begins to feel extraordinary. Step outside on a quiet evening and look up. The sky feels vast, open, almost infinite. It stretches from horizon to horizon, fading from blue to gold to black. It feels immense. And yet the layer of air responsible for every cloud, every breeze, every storm, and every drop of rain is astonishingly thin. Earth's atmosphere is a delicate envelope of gas wrapped around a rocky sphere. If the planet were shrunk to the size of a classroom globe, the part of the atmosphere where almost all weather occurs would be thinner than a layer of paint. That comparison is not poetic exaggeration. It is a matter of scale. This envelope is made primarily of nitrogen, which accounts for roughly 78% of the air by volume. Oxygen makes up about 21%. The remaining 1% is a mixture of gases including argon, carbon dioxide, neon, helium, methane, and trace amounts of others. Water vapor, which varies from near zero in cold polar air to several percent in humid tropical air, plays a surprisingly powerful role despite its relatively small fraction. Nitrogen is largely inert under normal atmospheric conditions. It provides stability, acting as a background gas. Oxygen supports respiration and combustion. Argon, chemically quiet, simply occupies space. Carbon dioxide, though present at a fraction of a percent, absorbs and emits infrared radiation, influencing Earth's temperature through the greenhouse effect. Water vapor, meanwhile, is the most dynamic ingredient of all. It changes phase easily, carrying energy as it evaporates and releases energy as it condenses. Air may feel weightless, but it has mass, and because it has mass, gravity pulls it toward Earth's surface. This pull gives rise to atmospheric pressure, the force exerted by the weight of air above a given point. At sea level, the average pressure is about 101,000 pascals, which is roughly equivalent to the weight of a column of air extending upward through the entire atmosphere, pressing gently on every square meter. That pressure exists because the atmosphere is in a state known as hydrostatic equilibrium. This principle describes a balance between two opposing forces. Gravity pulls air molecules downward, while the pressure gradient force pushes upward. When these forces balance, the atmosphere does not collapse onto the surface, nor does it drift off into space. Instead, it forms a stable gradient in which air becomes progressively thinner with height. As altitude increases, pressure decreases, density decreases. There are simply fewer air molecules in a given volume. By the time one reaches the summit of Mount Everest, atmospheric pressure is roughly 1/3 of what it is at sea level. This thinning of air is not abrupt but gradual, forming a smooth density gradient that extends upward for hundreds of kilometers. For clarity, scientists divide the atmosphere into layers based on temperature trends. Closest to the surface lies the troposphere. Above it sits the stratosphere. Higher still are the mesosphere, the thermosphere, and finally the exosphere, where the atmosphere fades into space. Weather happens almost entirely within the troposphere. The troposphere extends from the surface up to an average height of about 12 kilometers, though this varies with latitude and season. Near the equator, it can reach up to about 17 kilometers. Near the poles, it may be closer to 8 kilometers. Within this layer, temperature generally decreases with altitude at an average rate known as the environmental lapse rate, roughly 6.5 degrees Celsius per kilometer under typical conditions. That steady drop in temperature with height is crucial. It allows warm air near the surface to rise, cool, and sometimes condense into clouds. Without this temperature gradient, the vertical motion that drives weather would be dramatically altered. Above the troposphere lies the stratosphere, where temperature begins to increase with altitude due to the absorption of ultraviolet radiation by ozone molecules. This temperature inversion suppresses vertical mixing, which is one reason commercial aircraft cruise near its lower boundary. It is comparatively stable. Clouds and storms rarely intrude there. Higher layers, such as the mesosphere and thermosphere, experience extreme temperatures and interactions with solar radiation, but they play little direct role in daily weather. The troposphere remains the engine room. Within this lower layer, air is constantly in motion. Temperature differences create pressure differences. Pressure differences create wind. Water vapor condenses into droplets. Droplets gather into clouds. Energy is absorbed, transported, and released. At its core, weather is the redistribution of energy through the movement of air and water. This movement is governed by fundamental physical laws. The behavior of gases can be described by the ideal gas law, expressed in words as pressure multiplied by volume equals the number of moles multiplied by the gas constant multiplied by temperature. While the mathematics can be set aside for now, the principle is essential. When air is heated, its molecules move faster. The air expands, becomes less dense, and rises. When air cools, molecules move more slowly. The air contracts, becomes denser, and sinks. This simple relationship between temperature, pressure, and density underlies convection, the vertical motion that builds clouds and fuels storms. Gravity ensures that rising air eventually cools and slows. The pressure gradient force ensures that air flows from regions of higher pressure toward regions of lower pressure. Together, these forces create the dynamic patterns seen in winds, fronts, and circulation cells. The atmosphere is not chaotic in the sense of being lawless. It is structured, it is responsive, it follows thermodynamics, fluid dynamics, and conservation of energy with remarkable consistency. Consider a calm summer afternoon. The ground absorbs sunlight and warms. Air just above the surface heats, expands, and begins to rise. As it rises, pressure decreases. The air expands further and cools due to adiabatic cooling, which occurs when a parcel of air expands without exchanging heat with its surroundings. If that rising air cools to its dew point, water vapor condenses into tiny droplets, forming a cloud. That entire process is the atmosphere attempting to balance uneven heating. Weather begins with imbalance. The equator receives more solar energy than the poles. Land warms more quickly than ocean. Dark surfaces absorb more energy than bright ones. These differences create temperature gradients. Temperature gradients create pressure gradients. Pressure gradients create motion. Motion transports energy. Even the gentlest breeze is part of that transport. A passing cloud is a visible trace of invisible thermodynamics. A distant storm is the large-scale expression of the same principles that lift warm air from a sunlit pavement. Despite its thinness, the atmosphere contains enormous energy. A single mature thunderstorm can release energy comparable to several atomic bombs over its lifetime, not through explosion, but through the steady release of latent heat as water vapor condenses. That energy was originally absorbed from sunlight during evaporation. The sky then is not passive, it is active. It is a fluid system in constant adjustment. Understanding that thin layer of gases held delicately in hydrostatic equilibrium, shaped by gravity and temperature gradients, is the foundation for understanding everything that follows. Without this fragile envelope, there would be no clouds, no rain, no wind, no weather at all. It is easy to forget that life on Earth depends on this subtle balance. The atmosphere shields the surface from harmful ultraviolet radiation. It moderates temperature extremes. It provides oxygen for respiration and carbon dioxide for photosynthesis. It carries water across continents. All of it happens within a layer that, in planetary terms, is barely there, and within that thin, shifting layer, energy never stops moving. Far above the thin envelope of air surrounding Earth, beyond clouds and jet streams and even the faint edge of the thermosphere, there is a steady, relentless source of energy. It does not flicker in response to our storms. It does not pause when the sky turns grey. It shines outward in all directions every second with astonishing consistency. That source is the sun. At its core, the sun is not burning in the way a fire burns. It is powered by nuclear fusion. Deep within its interior, where temperatures reach roughly 15 million degrees Celsius and pressures are immense, hydrogen nuclei collide and fuse together. The dominant process in a star the size of the Sun is known as the proton-proton chain reaction. In this sequence of reactions, hydrogen nuclei combine step by step to form helium. Along the way, a small fraction of mass is converted into energy, according to Albert Einstein's mass-energy equivalence principle. That principle can be written in words as energy equals mass multiplied by the speed of light multiplied by the speed of light. Because the speed of light is extraordinarily large, even a tiny loss of mass produces an enormous release of energy. Every second, the Sun converts hundreds of millions of tons of hydrogen into helium. A few million tons of that mass are transformed directly into radiant energy. That energy travels outward from the Sun's core, first through its dense interior, then from its surface as electromagnetic radiation. It spreads through space in the form of visible light, infrared radiation, ultraviolet radiation, and smaller amounts of other wavelengths. A small fraction of that radiation reaches Earth. The average amount of solar energy arriving at the top of Earth's atmosphere, measured on a surface facing the Sun directly, is known as the solar constant. It is approximately 1360 watts per square meter. This value is not perfectly constant. It fluctuates slightly with solar activity, which is monitored carefully by space agencies such as NASA and the European Space Agency. But for understanding weather, it is stable enough to serve as a steady input of energy. When this incoming solar radiation reaches Earth, it is called insolation, short for incoming solar radiation. Insolation does not fall evenly across the planet. Because Earth is spherical, sunlight strikes the equatorial regions more directly than it does the poles. Near the equator, sunlight arrives at a steep angle, concentrating energy over a smaller surface area. Near the poles, sunlight arrives at a shallow angle, spreading the same energy over a much larger area. The result is that tropical regions receive significantly more energy per unit area than polar regions. Earth's axial tilt adds another layer of variation. The planet is tilted at about 23.5 degrees relative to its orbit around the Sun. This tilt produces the seasons. When one hemisphere is tilted toward the Sun, it receives longer daylight hours and more direct sunlight. 6 months later, the situation reverses. The combination of curvature and tilt ensures that solar heating is uneven in both space and time. Not all incoming sunlight is absorbed. Some of it is reflected back into space. The measure of how much sunlight a surface reflects is known as albedo. A bright surface has a high albedo. A dark surface has a low albedo. Fresh snow can reflect up to 80 or even 90% of incoming sunlight. Ice sheets in Antarctica and Greenland are highly reflective. By contrast, dark ocean water absorbs most of the sunlight that reaches it, reflecting only a small fraction. Forests absorb more energy than deserts. Deserts, with their pale sands, reflect more than dense vegetation but less than fresh snow. These differences matter. If a region reflects a large portion of sunlight, it remains cooler. If it absorbs most of the incoming radiation, it warms more efficiently. Oceans, which cover about 70% of Earth's surface, have a relatively low albedo and a high heat capacity. They absorb enormous amounts of energy and release it slowly. Land surfaces, especially dry ones, heat up and cool down more rapidly. NASA Earth science satellites, such as those in the clouds and the Earth's Radiant Energy System program, measure how much solar energy enters Earth's atmosphere and how much is reflected or emitted back into space. These measurements help scientists monitor Earth's energy balance. On average, the planet absorbs nearly as much energy as it radiates away. If that balance shifts, even slightly, global temperatures adjust over time. For weather, what matters most is that heating is uneven. The equator receives more energy than it loses. The poles lose more energy than they receive. This imbalance creates a temperature gradient between low and high latitudes, and temperature gradients are the seeds of motion. Warm air expands and becomes less dense. Cool air contracts and becomes denser. Where air is warm and less dense, surface pressure tends to be lower. Where air is cool and denser, surface pressure tends to be higher. These pressure differences are not arbitrary. They arise directly from uneven heating. Nature tends toward equilibrium. Excess energy in equatorial regions must be redistributed toward the poles. The atmosphere and the oceans share this task. In the atmosphere, this redistribution occurs through large-scale circulation patterns. Warm air rises near the equator. It moves poleward at higher altitudes. It cools and eventually sinks. This process is part of what is known as the Hadley Cell circulation. The root cause of that circulation is not wind itself, it is sunlight. Even small changes in solar input can have noticeable effects. During the day, land surfaces warm under direct sunlight, creating local pressure differences that generate sea breezes and land breezes along coastlines. Over longer timescales, seasonal shifts in insolation alter monsoon systems, influencing rainfall patterns that sustain billions of people. The energy driving all of these processes began as nuclear fusion in the Sun's core. It is easy to overlook the scale involved. The total power output of the Sun is on the order of 4 followed by 26 zeros watts. Only a tiny fraction of that energy reaches Earth, yet it is sufficient to power global wind systems, evaporate vast quantities of water, and sustain life. Every cloud owes its existence to evaporation powered by sunlight. Every gust of wind traces back to temperature differences ultimately created by solar radiation. Even the dramatic spirals of hurricanes draw their strength from warm ocean water heated by months of accumulated sunlight. Without continuous solar input, Earth's atmosphere would cool and stabilize. Winds would diminish. The hydrological cycle would slow. Weather, as it is known, would fade into stillness. Instead, the sun shines steadily. Energy arrives at the top of the atmosphere. Some is reflected by clouds and ice. Some is absorbed by land and sea. Some warms the air directly. Some drives evaporation. Some fuels convection. That steady input creates imbalance, and imbalance creates motion. The story of weather begins not with wind or rain, but with light travelling across space. A photon born in the sun's core may take thousands of years to reach the surface of the sun, bouncing from particle to particle within its dense interior. Yet once it escapes into space, it travels to Earth in just over 8 minutes. 8 minutes after leaving the sun, that energy may warm a patch of ocean, heat a stretch of desert, or strike the leaves of a forest. From that moment onward, the atmosphere responds. Stand still for a moment on a breezy day, and the movement of air feels simple. Wind brushes against skin, rustles leaves, nudges clouds across the sky. It can seem almost playful, as if air simply decided to wander. But air does not move on impulse, it moves because of physics. At the heart of that motion lies thermodynamics, the branch of physics that describes how heat and energy behave. Air is a mixture of gases made of molecules in constant motion. These molecules collide with one another, and with any surface they encounter. Temperature is a measure of the average kinetic energy of those molecules. When air warms, its molecules move faster. When air cools, they move more slowly. This difference in molecular motion changes the behavior of the air itself. When air is heated, its molecules spread apart slightly. The air expands. If it is free to move, that expansion reduces its density. Density simply means how much mass is contained within a given volume. Less dense air weighs less per unit volume than denser air. Gravity pulls more strongly on denser air because it contains more mass. So when a parcel of air becomes warmer and less dense than the air surrounding it, it experiences buoyancy. Buoyancy is the same principle that allows a hot air balloon to rise. The warmer air inside the balloon is less dense than the cooler air outside, so it floats upward. In the atmosphere, this vertical movement is called convection. Convection begins when the surface of Earth warms unevenly. Sunlight heats a stretch of land. The air touching that land warms as well. As it warms, it expands and becomes lighter than the surrounding air. That lighter air begins to rise. As it rises, cooler air from nearby flows in to replace it. That horizontal movement of air toward the rising column is the beginning of wind. Cooler air, being denser, tends to sink. When it sinks, it increases pressure near the surface. Rising air reduces pressure at the surface. These pressure differences are not abstract. They are measurable, and they are the immediate cause of wind. Air moves from regions of higher pressure to regions of lower pressure. This movement is driven by what is known as the pressure gradient force. A pressure gradient is simply a change in pressure across a distance. If one location has slightly higher atmospheric pressure than another nearby location, a gradient exists between them. The pressure gradient force acts in the direction from high pressure toward low pressure, pushing air along that gradient. The stronger the difference in pressure over a given distance, the stronger the force, and therefore the stronger the wind. To understand why temperature differences produce pressure differences, it helps to describe the ideal gas law in words. The ideal gas law can be expressed as pressure multiplied by volume equals the number of gas particles multiplied by the gas constant multiplied by temperature. This relationship connects pressure, temperature, density, and volume in a precise way. If temperature increases while the number of gas particles remains the same, either pressure must increase or volume must increase. In the open atmosphere, air is free to expand vertically. So when it warms, it tends to expand upward, rather than dramatically increasing pressure at the surface. As it expands, its density decreases. Cooler air, by contrast, contracts and becomes denser. Denser air near the surface contributes to higher surface pressure. Warmer, rising air contributes to lower surface pressure. These pressure differences, even when small, are enough to set the atmosphere in motion. Consider a difference of just a few millibars between two regions. That difference represents a measurable imbalance in the weight of air columns above those regions. The atmosphere responds by moving air toward equilibrium. It seeks balance. The concept that air has weight was not always obvious. In the 17th century, the Italian scientist Evangelista Torricelli conducted an experiment that changed understanding of the atmosphere. In 1643, he filled a glass tube with mercury and inverted it into a dish of mercury. Some of the mercury remained suspended in the tube, held up not by suction, as many believed at the time, but by the pressure of the air pushing down on the surface of the dish. Torricelli had invented the barometer. The height of the mercury column varied with changes in atmospheric pressure. For the first time, air pressure could be measured directly. This discovery laid the foundation for modern meteorology. Without pressure measurements, there could be no reliable forecasting, no mapping of high and low pressure systems, and no quantitative understanding of wind. When a barometer falls, it indicates decreasing atmospheric pressure. That often signals rising air and the approach of unsettled weather. When it rises, it suggests sinking air and generally more stable conditions. Behind these measurements lies the continuous interplay between temperature, density, and pressure. As warm air rises, it does not remain warm indefinitely. As it ascends, the surrounding pressure decreases. Lower pressure allows the rising air to expand. Expansion requires energy. That energy is drawn from the internal energy of the air itself, causing it to cool. This cooling without exchanging heat with the surrounding air is called adiabatic cooling. If the rising air cools enough, water vapor may condense into droplets, forming clouds. When condensation occurs, latent heat is released, adding energy back into the rising air and sometimes allowing it to rise even higher. This release of latent heat is one reason thunderstorms can grow tall and powerful. The entire process begins with a simple temperature difference. Air moves because it is trying to reduce imbalances. Heat creates density differences. Density differences create pressure differences. Pressure differences create motion. It is not only vertical motion that matters. Once air begins to move horizontally from high pressure toward low pressure, other forces influence its path. Earth's rotation introduces the Coriolis Effect, which causes moving air to deflect to the right in the northern hemisphere and to the left in the southern hemisphere. But even this rotational influence acts on air that is already in motion because of pressure gradients. The first cause remains uneven heating. The atmosphere behaves as a fluid. It flows according to the principles of fluid dynamics, described mathematically in the Navier-Stokes equations. While the full equations are complex, their essence is simple. Fluids accelerate when forces act upon them. In the atmosphere, the primary large-scale force initiating motion is the pressure gradient force. Every breeze felt at ground level is part of this continuous adjustment. Warm regions generate rising motion and lower pressure. Cooler regions generate sinking motion and higher pressure. Air responds by flowing between them. Even on a clear day with gentle winds, countless small convection cells may be rising and falling invisibly. Overheated pavement, Warm air shimmers upward. Over shaded grass, cooler air sinks. These small-scale motions combine into larger patterns. There is no need for drama in this process. The physics is steady and consistent. Air moves because temperature differences exist. Temperature differences exist because sunlight is unevenly distributed, and the laws governing gases ensure that differences in temperature translate into differences in density and pressure. From these simple principles emerges the constant motion of the sky. When warm air rises from a sunlit surface, it may feel like a small local event, a shimmer above asphalt, a gentle breeze along a shoreline. But scale that process upward, stretch it across thousands of kilometers, and something far more organized begins to appear. The atmosphere does not simply circulate in scattered random swirls. It organizes itself into broad, semi-stable circulation systems that span entire hemispheres. These patterns form because the equator consistently receives more solar energy than the poles, and because Earth rotates. Begin at the equator. Sunlight strikes this region more directly than anywhere else on the planet. As a result, air near the surface warms strongly, becomes less dense, and rises. This rising air creates a persistent belt of relatively low pressure encircling the globe. The air cannot rise forever. As it ascends, it cools through adiabatic expansion. Eventually, at high altitude within the troposphere, it begins to spread outward toward higher latitudes. This rising and poleward moving air forms the upper branch of a circulation loop known as the Hadley Cell, named after the 18th century British scientist George Hadley, who proposed an early model of tropical circulation. In this system, air rises near the equator, flows poleward at high altitude, cools and sinks around 30 degrees latitude, and then returns toward the equator near the surface. Where the air sinks at roughly 30 degrees north and south, surface pressure increases. These regions are associated with many of the world's deserts, including the Sahara and the Australian interior. Sinking air warms as it compresses, discouraging cloud formation. Clear skies and dry conditions dominate. From these subtropical high-pressure zones, air flows back toward the equator along the surface. But the path is not straight. Earth rotates from west to east. Because of this rotation, moving air experiences an apparent deflection known as the Coriolis Effect. The French mathematician and engineer Gaspard Gustave de Coriolis described this effect mathematically in 1835 while studying rotating systems. In the atmosphere, the Coriolis effect causes moving air to deflect to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection does not create wind, but it changes the direction of winds that are already moving due to pressure differences. As surface air flows from the subtropical highs back toward the equatorial low, the Coriolis effect turns it westward. The result is a steady pattern of winds known as the trade winds. In the northern hemisphere, these are called the northeast trade winds. In the southern hemisphere, they are the southeast trade winds. For centuries, these winds powered sailing ships across the Atlantic and Pacific Oceans. The Hadley Cell is only one part of the global circulation system. Between roughly 30 degrees and 60 degrees latitude lies another circulation loop known as the Ferrel Cell, named after American meteorologist William Ferrel. Unlike the Hadley Cell, which is driven primarily by strong equatorial heating, the Ferrel Cell is more complex and is influenced by interactions between tropical and polar air masses. In this mid-latitude region, surface air generally flows poleward from the subtropical highs toward lower pressure regions near 60 degrees latitude. Again, the Coriolis effect deflects this poleward moving air. In the northern hemisphere, it turns eastward, creating the prevailing westerlies. These westerlies dominate weather patterns across much of North America, Europe, and parts of Asia. Storm systems in these regions typically move from west to east, because they are steered by these winds. At around 60 degrees latitude, warmer air from the feral cell meets colder air descending from the polar regions. This boundary zone is associated with frequent storm development and shifting weather patterns. Closer to the poles, the polar cell completes the trio of major circulation loops. Cold, dense air sinks over the poles, creating high surface pressure. From there, air flows equatorward along the surface. As it moves, the Coriolis Effect deflects it westward, forming the polar easterlies. These winds are typically weaker and more variable than the trade winds or westerlies, but they play a role in shaping polar weather. Together, the Hadley cells, feral cells, and polar cells create a three-cell model of atmospheric circulation in each hemisphere. While reality is more complex than this simplified model, it provides a powerful framework for understanding how energy moves from equator to pole. At the equator, where the two Hadley cells converge, lies a particularly important region known as the Intertropical Convergence Zone, often abbreviated as the ITCZ. This is a belt of low pressure where trade winds from both hemispheres meet. As they converge, air is forced upward. Rising air cools, water vapor condenses, and towering cumulonimbus clouds often develop. The ITCZ is associated with heavy rainfall, thunderstorms, and deep convection. It shifts northward and southward with the seasons, following the region of maximum solar heating. This seasonal migration influences monsoon systems and rainfall patterns across Africa, South America, and South Asia. The Intertropical Convergence Zone is sometimes called the doldrums, because surface winds can be relatively weak there, especially when vertical motion dominates. Historically, sailing ships could become stranded in these calm conditions, waiting for wind while surrounded by dramatic storm clouds rising overhead. The three-cell circulation pattern is not static. It fluctuates with seasons, ocean temperatures, and long-term climate variations. Yet its broad structure remains recognizable. Organizations such as the World Meteorological Organization coordinate global observations to monitor these circulation patterns. Satellites track cloud movements, temperature gradients, and wind speeds. Weather balloons launched daily around the world measure atmospheric conditions at various altitudes. These data are combined to create a dynamic picture of planetary circulation. At high altitudes, near the boundaries between these cells, fast-flowing currents of air known as jet streams form. These jet streams arise partly because of strong temperature contrasts between air masses and are shaped by the Coriolis effect. They act as atmospheric rivers, guiding storm systems across continents. All of these patterns originate from the same fundamental imbalance. More energy enters the equatorial region than the polar regions receive. The atmosphere responds by attempting to redistribute that excess heat. Warm air rises, moves poleward, cools, sinks, and returns. The process repeats continuously. Even though individual storms may appear chaotic, the large-scale structure of atmospheric circulation is remarkably organized. It is shaped by thermodynamics, fluid dynamics, and planetary rotation working together. A breeze felt at mid-latitude may trace its origin back to the sinking branch of a Hadley cell thousands of kilometers away. A storm sweeping across the North Atlantic may be guided by the prevailing westerlies that arise from the feral cell. Rainfall in equatorial regions may be tied directly to the shifting position of the Intertropical Convergence Zone. The sky, viewed on a planetary scale, reveals vast looping patterns that connect deserts to rainforests, polar ice to tropical seas. Air moves not only because it is warm or cool, but because Earth is a rotating sphere receiving uneven sunlight. The result is a structured circulation system that spans hemispheres, linking local breezes to global flows. Air can move because of temperature differences alone, but without water, weather would be far quieter. Water is the atmosphere's quiet amplifier. It begins as liquid in oceans, lakes, rivers, soil, and even on the surface of leaves. When sunlight warms these surfaces, some water molecules gain enough energy to escape into the air as vapor. This process is called evaporation. It requires energy. That energy is absorbed from the surrounding environment, cooling the surface slightly as water transitions from liquid to gas. Evaporation is only one part of a continuous cycle. Water vapor rises with warm air. As that air cools at higher altitudes, the vapor may condense back into liquid droplets or freeze into ice crystals. This is condensation. When droplets grow large enough, they fall as precipitation, which may take the form of rain, snow, sleet, or hail. Water that reaches the ground may flow across land as runoff, seep into soil as groundwater, or return directly to oceans. This continuous movement of water between surface and atmosphere is known as the hydrological cycle, or simply the water cycle. At first glance, this cycle seems straightforward. Water evaporates, forms clouds, and falls again. But hidden within these phase changes is a powerful source of energy. When water evaporates, it absorbs heat from its surroundings without raising its temperature. This energy is stored in the molecular bonds of water vapor. It is called latent heat. The term latent means hidden, because the energy is not expressed as temperature at that moment. It is carried invisibly within the vapor. When water vapor later condenses into liquid droplets, that stored energy is released back into the surrounding air as heat. This release of latent heat can warm rising air parcels, reduce their density further, and allow them to rise higher than they otherwise would. The amount of energy involved is substantial. To evaporate 1 kilogram of water at typical atmospheric temperatures requires roughly 2.5 million joules of energy. That is enough energy to power a small electric heater for many minutes. Multiply that by the vast quantities of water evaporated from tropical oceans each day, and the scale becomes enormous. In effect, evaporation stores solar energy in water vapor. Condensation releases that energy later, often at higher altitudes. This process is central to storm development. A developing thunderstorm over a warm ocean does not draw its strength directly from warm air alone. It feeds on the release of latent heat as water vapor condenses inside rising clouds. That released energy fuels further upward motion, deepening the storm. Without water vapor, the atmosphere would still circulate. Winds would still blow due to pressure differences, but storms would be weaker. Temperature contrasts would be less dramatic. The sky would be calmer. To understand how water vapor behaves in air, it is necessary to define humidity. Humidity refers to the amount of water vapor present in the air. It can be expressed in several ways. Absolute humidity measures the actual mass of water vapor in a given volume of air. More commonly, meteorologists use relative humidity. Relative humidity describes how close the air is to saturation. It is the ratio of the current amount of water vapor in the air to the maximum amount the air could hold at that temperature, expressed as a percentage. Warm air can hold more water vapor than cold air. This relationship is described by the Clausius-Clapeyron relation, which explains how the saturation vapor pressure of water increases with temperature. In practical terms, for every increase of about 10 degrees Celsius, the maximum amount of water vapor air can hold increases significantly. If relative humidity reaches 100%, the air is saturated. At that point, additional cooling or added moisture will cause condensation. The temperature at which air becomes saturated is called the dew point. If air cools to its dew point, water vapor begins to condense into tiny droplets. On cool mornings, dew forms on grass when the surface temperature drops below the dew point of the surrounding air. The same principle operates on a larger scale in the sky when rising air cools to its dew point and forms clouds. Humidity influences how weather feels as well as how it behaves. High humidity reduces the rate at which sweat evaporates from skin, making warm conditions feel hotter. Low humidity allows rapid evaporation, creating a cooling sensation even at moderate temperatures. Beyond comfort, humidity plays a critical role in atmospheric stability. Moist air rising in the atmosphere cools at a different rate than dry air, because of latent heat release. When condensation occurs, the released heat partially offsets cooling, making moist air more buoyant than dry air under certain conditions. This difference is described by the moist adiabatic lapse rate, which is lower than the dry adiabatic lapse rate. In the late 19th and early 20th centuries, the Norwegian scientist Wilhelm Bjerknes recognized the importance of combining thermodynamics with fluid dynamics to understand weather systems. He proposed that the atmosphere could be treated as a physical system governed by mathematical equations describing motion, heat transfer, and moisture. His work laid the foundation for dynamic meteorology, which treats weather as the outcome of interacting physical laws rather than isolated observations. Bjerknes understood that moisture was not an afterthought, it was integral. Water vapor altered density, released energy, and influenced pressure patterns. To predict weather, one had to account for humidity and phase changes. When water vapor condenses in a rising air mass, the release of latent heat can lower surface pressure further, intensifying the pressure gradient and strengthening winds. In tropical cyclones, warm ocean water provides continuous evaporation. As moist air spirals inward and rises, massive amounts of latent heat are released in the storm's core. This additional heat lowers central pressure and accelerates circulation. Water vapor does not initiate motion by itself. That role belongs to uneven heating and pressure gradients. But water vapor magnifies the consequences of motion. It deepens low-pressure systems. It fuels convection. It shapes precipitation patterns. Even in colder climates, moisture remains influential. Snowstorms form when moist air is lifted and cooled below freezing. Ice crystals grow around microscopic particles, eventually falling as snow. The same latent heat principles apply, though the phase changes may involve freezing rather than condensation alone. Globally, oceans provide the majority of atmospheric water vapor. The tropics, where sea surface temperatures are highest, supply especially large amounts. From there, winds transport moisture across continents. Rainforests depend on this transport. Mountain ranges intercept moist air and force it upward, creating orographic precipitation. Water links surface and sky in a continuous exchange. Without water vapor, the atmosphere would resemble that of Mars more closely, thin and dry, with minimal cloud formation and little precipitation. On Earth, the abundance of liquid water and moderate temperatures allow water to exist in all three phases: solid, liquid, and gas. This versatility underlies the richness of weather. Each time a cloud forms, energy stored during evaporation is being released. Each time rain falls, that energy has completed part of its journey through the atmosphere. Moisture does not merely accompany weather, it intensifies it. Air moves because of pressure gradients created by uneven heating. But when that moving air carries water vapor, it carries stored energy as well. As that vapor condenses, energy is released, reinforcing upward motion and sometimes transforming gentle convection into towering storm systems. The sky's most dramatic displays often owe their strength to invisible water changing phase. Even on a calm day, humidity quietly shapes atmospheric behavior. It determines when clouds will form, how high they will grow, and how much energy they may release. It controls the transition from invisible vapor to visible cloud. Water is common, ordinary, familiar. Yet within the atmosphere it acts as a powerful amplifier, converting sunlight into motion and motion into weather. Look up at a cloud and it seems almost solid. It has shape, edges, texture. It casts shadows. It glows gold at sunset and blushes pink at dawn. Yet a cloud is not solid at all. It is a vast collection of tiny water droplets or ice crystals suspended in air, so small and so light that they can float for long periods before falling. A cloud forms when invisible water vapor becomes visible. For that to happen, air must cool to its dew point, the temperature at which it becomes saturated and condensation begins. As rising air expands, it cools through adiabatic cooling. This cooling happens because as air moves into regions of lower pressure, it expands, and expansion requires energy. That energy is drawn from the air's internal heat, lowering its temperature without exchanging heat with the surrounding environment. Once the temperature drops to the dew point, water vapor molecules begin to cluster together. But they do not simply gather spontaneously into droplets. In the real atmosphere, condensation almost always occurs around tiny particles known as condensation nuclei. Condensation nuclei are microscopic solid or liquid particles suspended in air. They may be specks of dust lifted from dry soil, grains of sea salt thrown upward by breaking waves, soot from combustion, pollen from plants, or sulfate particles formed by volcanic eruptions. Even in seemingly clear air, billions of these aerosol particles float invisibly. Water vapor molecules are attracted to these particles. They cling to their surfaces, forming the first microscopic droplets. Without condensation nuclei, cloud formation would require much higher humidity levels, and clouds would be far less common. As more water vapor condenses, droplets grow. In a typical cloud, droplets may measure only about 10 micrometers in diameter. That is far smaller than a raindrop. A raindrop must grow roughly 100 times larger in diameter before gravity can overcome the upward motions keeping it suspended. Clouds, then, are visible evidence that air has cooled and reached saturation. They mark regions where thermodynamics and motion intersect. Different lifting mechanisms bring air to the point of condensation. Convective lifting occurs when the surface warms unevenly. A patch of land heated strongly by sunlight warms the air above it. That air becomes buoyant and rises. As it rises, it cools adiabatically. If it reaches its dew point, condensation begins, and a cumulus cloud may form. These are the familiar puffy clouds often seen on warm afternoons, with flat bases and rounded tops. Orographic lifting happens when air is forced upward by terrain. When moist air encounters a mountain range, it cannot pass through the rock. It must rise. As it ascends along the mountain slope, it cools. Clouds may form on the windward side, often bringing rain or snow. On the leeward side, descending air warms and dries, creating a rain-shadow effect. Frontal lifting occurs when two air masses of different temperatures meet. Along a cold front, denser cold air wedges beneath warmer air, forcing the warm air to rise rapidly. Along a warm front, warmer air gradually rises over cooler air. In both cases, rising motion leads to cooling and potential cloud formation. These lifting mechanisms differ in detail, but they share the same underlying principle. Rising air cools, and cooling air may reach saturation. Clouds are categorized according to their shape and altitude. The system widely used today traces back to the work of Luke Howard, an English chemist and amateur meteorologist who, in the early 19th century, proposed a classification based on Latin terms. His approach, introduced in 1802, provided a structured language for describing the sky. Cumulus means heap. Cumulus clouds appear as isolated cotton-like heaps with well-defined edges. They often indicate localized convection. Stratus means layer. Stratus clouds form uniform, grey sheets that can cover large areas of sky, sometimes bringing light drizzle or overcast conditions. Cirrus means curl. Cirrus clouds form high in the atmosphere, composed primarily of ice crystals. They appear as thin, wispy streaks, often signalling changes in weather patterns at higher altitudes. Cumulonimbus combines the heap of cumulus with the rain-bearing nature of nimbus. These are towering storm clouds that can reach heights of more than 10 kilometers, sometimes penetrating into the lower stratosphere. Within them, strong updrafts and downdrafts interact, producing heavy rain, lightning, hail, and occasionally tornadoes. The classification may sound poetic, but it reflects physical differences in formation and structure. High-altitude clouds such as cirrus form in colder regions of the upper troposphere, where temperatures are well below freezing. Mid-level clouds, including altostratus and altocumulus, occupy intermediate heights. Low-level clouds such as stratus and nimbostratus form closer to the surface. Clouds are not merely decorative. They reveal what the atmosphere is doing. A line of cumulus clouds forming over a heated field signals active convection. A spreading deck of stratus may indicate widespread lifting along a frontal boundary. Thin cirrus streaks racing overhead can hint at strong winds in the upper troposphere, often associated with jet streams. Cloud bases form at the level where rising air reaches its dew point. This height can often be estimated by comparing surface temperature and dew point temperature. A small difference suggests low cloud bases and humid conditions. A larger difference indicates drier air and higher cloud formation levels. Clouds also influence Earth's energy balance. Thick, low clouds reflect significant amounts of incoming solar radiation, increasing planetary albedo and cooling the surface. High, thin cirrus clouds, by contrast, can trap outgoing infrared radiation, contributing to warming. Their role in climate feedback remains an active area of research within atmospheric science. Despite their visible presence, clouds are mostly empty space. Even a dense cloud may contain only a few grams of liquid water per cubic meter. What makes it visible is not density in the sense of mass per volume, but the scattering of sunlight by countless tiny droplets. Clouds translate invisible thermodynamic processes into visible forms. When air rises and cools, a cloud appears. When air sinks and warms, clouds dissipate as droplets evaporate back into vapor. The sky becomes clear again, though the underlying physics continues. A cloud drifting overhead is a marker. It shows where air is ascending, where moisture is condensing, where latent heat is being released. It reveals vertical motion that would otherwise remain unseen. In this way, clouds serve as signposts of atmospheric behavior. They are the visual language of thermodynamics and motion, written across the sky in shifting shapes. There are days when the sky feels balanced and still. Clouds drift lazily. Air rises gently and then settles again. Nothing dramatic unfolds, and yet, under slightly different conditions, that same sky can erupt into towering storms, lightning, and torrential rain. The difference lies in atmospheric instability. Instability describes the tendency of air to continue rising once it has been lifted. To understand it clearly, it helps to compare a rising parcel of air to the surrounding environment. If a parcel of air is lifted slightly and becomes warmer than the air around it, it will be less dense and continue to rise on its own. If it becomes cooler than its surroundings, it will sink back to where it started. The key comparison is between the temperature of the rising air and the temperature of the surrounding atmosphere at the same height. The rate at which temperature decreases with altitude in the surrounding atmosphere is called the environmental lapse rate. On average, in the troposphere, this decrease is about 6.5 degrees Celsius per kilometre, though it varies from place to place and day to day. A rising parcel of dry air cools at what is called the dry adiabatic lapse rate, approximately 10 degrees Celsius per kilometre. If the air is moist and condensation occurs, the cooling rate slows because latent heat is released. This reduced rate is known as the moist adiabatic lapse rate, and it varies with temperature and moisture content, often around 5 to 7 degrees Celsius per kilometre. Instability occurs when the environmental lapse rate is steeper than the lapse rate of the rising parcel. In simpler terms, if the surrounding air cools very quickly with height, a rising parcel can remain warmer than its environment as it ascends. When that happens, buoyancy increases and upward motion accelerates. In contrast, if the atmosphere cools slowly with height, rising air soon becomes cooler than its surroundings and sinks back down. That condition is called stability. Even small differences in temperature gradients can determine whether the sky remains quiet or erupts into storms. Meteorologists use a measure called convective available potential energy, often abbreviated as CAPE, to quantify how much energy is available to fuel rising air. CAPE represents the amount of buoyant energy that an air parcel would gain if lifted through an unstable layer of the atmosphere. CAPE is measured in joules per kilogram. On calm days, values may be very low, near zero. On days with strong thunderstorm potential, CAPE can reach into the thousands of joules per kilogram. Higher values indicate greater potential for vigorous updrafts. The presence of CAPE does not guarantee a storm. It represents potential energy, not automatic motion. A trigger is still required to lift air to the level where buoyancy can take over. That trigger may be surface heating, a frontal boundary, or air forced upward by terrain. Once air begins rising and reaches a level where it becomes warmer than its surroundings, instability can amplify the motion dramatically. Thunderstorm formation unfolds in recognizable stages. First comes the cumulus stage. Warm, moist air near the surface begins to rise due to convection. As it ascends, it cools and reaches saturation. A cumulus cloud forms. If instability is modest, the cloud may remain small and dissipate. If instability is strong, the rising air continues upward with increasing speed. As condensation occurs, latent heat is released. This added warmth enhances buoyancy, allowing the updraft to strengthen further. The cloud grows taller, sometimes reaching heights of 10 to 15 kilometers. When it reaches the upper troposphere, it may spread outward, forming the characteristic anvil shape of a cumulonimbus cloud. This is the mature stage of a thunderstorm. Within the cloud, powerful updrafts carry droplets and ice particles upward. At the same time, precipitation begins to form. When raindrops or ice particles grow heavy enough, they fall. As they descend, they drag air downward, creating downdrafts. The storm becomes a dynamic system of rising and sinking air. Collisions between ice particles in the upper portions of the cloud lead to charge separation. Positive and negative electrical charges accumulate in different regions. When the electrical potential difference becomes strong enough, lightning occurs, equalizing the imbalance. Thunder is the sound of rapidly expanding air heated by the lightning channel. Eventually the downdrafts dominate. Cooler air spreads out along the surface, cutting off the supply of warm, moist air feeding the storm. The updraft weakens and the storm dissipates. The entire life cycle may last less than an hour for a simple thunderstorm, though more complex systems can persist much longer. Research from the National Severe Storms Laboratory in the United States has shown how subtle variations in temperature, humidity, and wind shear can transform ordinary thunderstorms into severe ones. Wind shear, the change of wind speed or direction with height, can tilt and organize updrafts, preventing downdrafts from choking them off. Under the right conditions, this can lead to supercell thunderstorms, which are capable of producing large hail, damaging winds and tornadoes. It is remarkable that differences of only a few degrees in temperature or modest changes in humidity can determine whether the atmosphere remains placid or generates violent storms. This sensitivity arises because buoyancy depends directly on temperature differences between an air parcel and its surroundings. A parcel that is only 1 or 2 degrees warmer than the surrounding air can accelerate upward rapidly if the environment supports instability. The released latent heat from condensation can then magnify that small initial difference into a powerful updraft. Weather systems are nonlinear. Small changes in initial conditions can produce disproportionately large outcomes. A slight increase in surface temperature can raise Cape values significantly. A modest shift in wind shear can alter storm structure. What begins as a barely perceptible temperature gradient near the surface can evolve into a towering cumulonimbus cloud, reaching the edge of the stratosphere. This amplification does not violate physical laws. It follows them precisely. The energy involved in a thunderstorm ultimately comes from solar heating and stored latent heat in water vapor. Instability simply determines how efficiently that energy is converted into motion. Atmospheric instability is not inherently dangerous. It is a measure of potential. On many days, instability is present, but no trigger occurs. The sky remains clear despite the stored energy. But when rising air taps into that potential, motion accelerates, updrafts intensify, clouds deepen, electrical charges separate, rain falls heavily. Calm air can become violent motion because the atmosphere is a fluid system sensitive to gradients in temperature and moisture. The same thermodynamic principles that lift a small cumulus cloud can, under stronger instability, generate severe storms. Understanding instability explains how the sky can shift so rapidly from tranquil blue to rumbling grey. Air moves because of pressure differences. It rises because of buoyancy. It accelerates because of instability. And when that rising air begins to rotate, even more complex structures can emerge. When air rises strongly over a warm ocean and surface pressure begins to fall, something subtle but powerful can happen. The atmosphere does not simply pull air inward in straight lines. On a rotating planet, inward motion curves. At the center of a developing low-pressure system, air converges from surrounding regions. As surface pressure drops, more air flows toward that center. Under calm, non-rotating conditions, the flow would move directly inward. But Earth rotates from west to east, and this rotation alters the path of moving air through the Coriolis Effect. In the northern hemisphere, air moving toward low pressure is deflected to the right. In the southern hemisphere, it is deflected to the left. The result is rotation. Around a low-pressure system in the northern hemisphere, winds spiral inward counterclockwise. In the southern hemisphere, they spiral clockwise. This organized rotation around a center of low pressure is called cyclonic circulation. The term cyclone simply refers to a rotating storm system centered on low pressure. It does not describe strength by itself, it describes structure. As air spirals inward, it does not pile up at the center. It rises. Rising air cools. Water vapor condenses. Latent heat is released. That released heat warms the air column above the center, lowering surface pressure further. Lower pressure strengthens the pressure gradient. Stronger gradients increase wind speeds. Increased wind speeds enhance convergence. A feedback loop begins. When this feedback becomes organized over warm ocean water, a tropical cyclone can form. The same type of storm carries different names depending on location. In the Atlantic Ocean and the northeastern Pacific Ocean, it is called a hurricane. In the northwestern Pacific Ocean, it is called a typhoon. In the Indian Ocean and parts of the southern Pacific, it is generally referred to as a cyclone. The physical processes are the same, only the geography changes. For a tropical cyclone to develop, several conditions must be present. First, sea surface temperatures must typically be at least about 26 to 27 degrees Celsius, over a substantial depth. Warm water supplies energy through evaporation. The deeper the warm layer, the more sustained the energy supply. Second, the atmosphere above the ocean must be unstable enough to support deep convection. Rising air must be able to continue ascending without being suppressed by stable layers. Third, vertical wind shear must be relatively low. Vertical wind shear refers to changes in wind speed or direction with height. If winds at upper levels are much stronger or oriented differently than those near the surface, they can disrupt the vertical alignment of a developing storm. Strong shear can tilt or tear apart the convection before it organizes. Fourth, a pre-existing disturbance is usually required. This might be a tropical wave, which is a weak area of low pressure moving westward through the tropics. The disturbance provides initial rotation and convergence. When these ingredients combine, clusters of thunderstorms begin to organize around a central low-pressure area. As latent heat is released within these thunderstorms, the central pressure drops further. Air flows inward more rapidly. The Coriolis effect causes that inflow to rotate more tightly. Eventually, a well-defined eye may form at the center. The eye is a region of relatively calm conditions and lower cloud cover. It forms because air in the core rises strongly in a ring known as the eye wall, then sinks gently in the center. Surrounding the eye wall contains the strongest winds and heaviest rainfall. Wind speeds increase as the pressure gradient intensifies. The storm becomes a highly organized energy system, drawing heat from warm ocean water and converting it into kinetic energy of wind and potential energy of rising air. The Saffir-Simpson hurricane wind scale classifies hurricanes based on their sustained wind speeds. A Category 1 hurricane has sustained winds beginning at 74 miles per hour. The scale rises through Category 5, which includes storms with sustained winds exceeding 157 miles per hour. The scale does not directly measure rainfall or storm surge, though those hazards often accompany stronger storms. The National Hurricane Center, part of the National Oceanic and Atmospheric Administration in the United States, monitors tropical cyclones in the Atlantic and Eastern Pacific. Using satellites, aircraft reconnaissance, ocean buoys, and computer models, forecasters track storm intensity and predict movement. Similar agencies operate in other ocean basins around the world. Despite their destructive potential, tropical cyclones follow understandable thermodynamic principles. They act as heat engines. Warm, moist air rises and releases latent heat. Cooler air sinks at the periphery. The system redistributes heat from the ocean surface upward and outward. The maximum theoretical intensity of a tropical cyclone depends partly on sea surface temperature and atmospheric conditions. In essence, the greater the temperature difference between the warm ocean surface and the colder upper atmosphere, the greater the potential energy available to drive convection. A mature tropical cyclone can release energy at a rate comparable to several hundred times the world's electrical generating capacity, though most of that energy is tied up in latent heat and is not directly available for human use. The winds represent only a fraction of the total energy flow. As long as the storm remains over warm water and vertical wind shear remains weak, it can maintain or even increase its intensity. Once it moves over cooler water or land, its energy supply diminishes. Friction with land surfaces disrupts the circulation. Without continuous evaporation feeding the system, the storm gradually weakens. Cyclonic rotation is not limited to the tropics. Low-pressure systems in mid-latitudes also rotate, though their structure differs. Tropical cyclones are primarily driven by latent heat release and warm ocean energy. Mid-latitude cyclones are driven more by horizontal temperature contrasts between air masses. Still, the underlying principle remains consistent. Low pressure draws air inward. Earth's rotation curves that inflow. Rising motion at the center sustains the system. Energy released through condensation reinforces the pressure drop. Rotation adds structure to motion. Without rotation, air would simply rush inward and upward, then disperse. With rotation, the flow organizes into spirals. Bands of rain wrap around the center. Winds strengthen along curved paths. The storm becomes coherent. The sight of a tropical cyclone from space reveals symmetry. Broad cloud bands arc gracefully around a central eye. The pattern appears almost elegant, yet beneath that symmetry lies intense motion, driven by energy transfer between ocean and atmosphere. Large rotating storms are not chaotic explosions. They are organized responses to imbalances in heat and pressure. They represent the atmosphere's attempt to redistribute energy efficiently across the planet. As these rotating systems move poleward, they eventually encounter different temperature gradients and interact with other circulation patterns. There, new types of cyclones take shape, driven not only by warm oceans but by contrasts between warm and cold air masses across entire continents. In the middle latitudes, weather often feels changeable. A bright morning can give way to afternoon rain. A mild day can be followed by a sharp drop in temperature overnight. These shifts are rarely random. They're usually tied to boundaries in the atmosphere known as fronts. A front is a transition zone between two air masses with different temperatures and often different humidity levels. An air mass is a large body of air that has relatively uniform temperature and moisture characteristics. Some form over cold continental interiors. Others develop over warm oceans. When these air masses move and meet, a front forms at their boundary. A cold front occurs when a colder, denser air mass advances toward a warmer one. Because cold air is heavier, it wedges underneath the warm air and forces it upward. This upward motion can be abrupt. Warm air lifted rapidly along a cold front may cool quickly, condense, and produce narrow bands of intense precipitation. Thunderstorms are common along strong cold fronts, especially in spring and summer. After the front passes, temperatures typically drop, winds shift direction, and skies often clear. A warm front forms when a warmer air mass moves toward colder air. Because warm air is lighter, it cannot easily push the cold air out of the way at the surface. Instead, it gradually rises over the colder air in a process known as overrunning. This lifting is gentler and more widespread than along a cold front. Warm fronts are often associated with layered clouds such as altostratus and nimbostratus, bringing steady precipitation over broad regions. Temperatures rise gradually as the front passes. A stationary front occurs when neither air mass advances significantly. The boundary stalls. Clouds and precipitation may linger for extended periods along the front, sometimes bringing prolonged rainfall. An occluded front develops later in the life cycle of the mid-latitude storm. It forms when a faster-moving cold front overtakes a warm front. In this process, the warm air that once lay between them is lifted entirely off the ground. The surface system becomes dominated by cooler air masses, and the storm often begins to weaken. These frontal structures are central to mid-latitude weather patterns. Their behaviour was clarified in the early 20th century by the Bergen School of Meteorology in Norway. Led by scientists such as Wilhelm Bjerknes, and later his colleagues, the Bergen School developed the polar front theory. This theory proposed that mid-latitude storms form along a boundary separating cold polar air from warmer subtropical air, known as the polar front. According to polar front theory, waves can develop along this boundary. A small disturbance along the polar front may cause warm air to move poleward on one side and cold air to move equatorward on the other. This wave grows into a cyclonic circulation. As the system intensifies, distinct cold and warm fronts emerge. Over time, the cold front catches up to the warm front, creating an occlusion and eventually lead into the storm's decay. This conceptual model remains foundational in meteorology. Mid-latitude storms, often called extratropical cyclones, differ from tropical cyclones in their energy source. Tropical cyclones draw energy primarily from warm ocean water and latent heat release. Extratropical cyclones draw energy from horizontal temperature contrasts between air masses. This contrast is known as baroclinicity. Where strong temperature gradients exist, especially along the polar front, potential energy is stored in the atmosphere. When a disturbance develops, that energy can be converted into kinetic energy, strengthening winds and deepening low pressure. Extratropical cyclones can span thousands of kilometers. Their cloud patterns are typically comma-shaped when viewed from satellites. They may bring a wide range of weather: heavy snow on the cold side, rain near the warm front, thunderstorms along the cold front, and clearing skies behind it. Unlike tropical cyclones, extratropical cyclones often intensify as they move over land. Their development is closely tied to the contrast between cold, continental air and warmer oceanic or subtropical air. Season plays a major role in shaping these systems. In winter, the temperature difference between equator and pole is greater than in summer. Cold air masses strengthen over continents. The polar front becomes sharper. Stronger temperature gradients support more vigorous mid-latitude storms. Winter cyclones can deepen rapidly, sometimes undergoing what meteorologists call explosive cyclogenesis, where central pressure falls dramatically within 24 hours. In summer, temperature contrasts are generally weaker in the mid-latitudes, leading to fewer intense extratropical cyclones. However, localized convection and frontal interactions can still produce significant weather. Storm tracks, the preferred paths along which these systems travel, tend to follow the prevailing westerlies. These winds steer storms from west to east across North America, Europe, and parts of Asia. Coastal regions often experience frequent frontal passages because of these recurring storm tracks. Everyday weather in temperate regions is often the visible expression of these frontal interactions. A gradual thickening of clouds during the day may signal an approaching warm front. A sudden gust of wind and a sharp line of dark clouds may indicate a cold front. A shift in wind direction, accompanied by falling pressure measured by a barometer, may suggest a developing low-pressure system nearby. These changes are governed by the same physical principles described earlier. Temperature differences create density differences. Density differences create pressure gradients. Pressure gradients generate wind. Along frontal boundaries, these gradients are especially pronounced. Extratropical cyclones are not merely random swirls of cloud. They are organized systems born from temperature contrasts across large regions. They convert stored potential energy along the polar front into motion and weather. Even when skies appear calm, the boundaries between air masses may be shifting quietly overhead. The interaction between warm and cold air remains central to mid-latitude weather. Above these surface systems, powerful rivers of air flow at high altitude, shaping their paths and intensity. The next layer of understanding lies there, where wind speeds increase dramatically, and the atmosphere reveals another level of structure. Far above the surface, well above the clouds that bring rain and snow, narrow bands of wind race around the planet at extraordinary speeds. These are the jet streams. A jet stream is a fast-flowing, relatively narrow current of air found in the upper levels of the troposphere, typically near the boundary with the stratosphere. Wind speeds within these currents commonly exceed 100 km per hour, and in some cases can surpass 300 km per hour. For comparison, that is faster than many commercial aircraft cruise speeds relative to the ground when flying with the wind. Jet streams form primarily because of strong horizontal temperature gradients in the atmosphere. Where large temperature contrasts exist between air masses, especially along the polar front, pressure surfaces in the upper atmosphere tilt. Warm air expands vertically more than cold air. This means that at a given altitude, pressure tends to be higher over warmer regions and lower over colder regions. These differences create strong pressure gradients at high altitudes. Air accelerates in response to these upper-level pressure gradients. Because the atmosphere is rotating with Earth, the Coriolis effect turns this accelerating air, balancing the pressure gradient force with what is known as the Coriolis force. When these forces reach equilibrium, the wind flows parallel to the isobars, forming what meteorologists call geostrophic flow. The result is a concentrated band of high-speed wind aligned roughly west to east. The strongest and most persistent of these is the polar jet stream, found near 60 degrees latitude in both hemispheres. A subtropical jet stream also exists closer to 30 degrees latitude, associated with the descending branch of the Hadley Cell. The presence and strength of jet streams vary with the seasons. In winter, when the temperature contrast between equator and pole is greatest, the polar jet stream tends to strengthen. In summer, when that contrast weakens, the jet often becomes less intense. The shape of the jet stream is not perfectly straight. It undulates in large waves that can extend thousands of kilometers. These undulations are known as Rossby waves, named after the Swedish-American meteorologist Carl Gustaf Rossby, who in the 1930s described their dynamics mathematically. Rossby waves arise because of the conservation of potential vorticity in a rotating fluid. As air moves northward or southward, the Coriolis parameter changes with latitude. To conserve angular momentum, the flow adjusts by forming large-scale waves. These waves create ridges, where the jet stream bends poleward, and troughs, where it dips equatorward. Ridges are often associated with high pressure and relatively calm, warmer conditions beneath them. Troughs are commonly associated with low pressure and more unsettled weather. The position of the jet stream strongly influences storm tracks. Extratropical cyclones tend to form and intensify beneath jet stream troughs, where upper-level divergence promotes rising motion at the surface. The jet stream acts as a steering current, guiding storms across continents. A shift in the jet stream's path can alter weather patterns dramatically. If the jet stream shifts northward, a region may experience prolonged warmth and dry conditions beneath a persistent ridge. If it dips southward, colder air from higher latitudes may surge equatorward, bringing unseasonably cool temperatures. In some cases, Rossby waves become amplified and slow-moving. When this happens, weather patterns can become blocked. A blocking pattern occurs when a high-pressure ridge becomes stationary, preventing normal west to east movement of weather systems. This can lead to extended heat waves, droughts, or prolonged rainfall events. Jet stream variability has been linked to certain extreme weather events. For example, when the jet stream forms deep troughs, cold polar air can plunge far southward, producing intense winter cold outbreaks. Conversely, strong ridges can trap hot air in place, contributing to heat waves. Research continues into how changes in Arctic temperatures may influence jet stream behavior. Some studies suggest that reduced sea ice and warming in the Arctic could weaken the temperature gradient between pole and mid-latitudes, potentially altering jet stream patterns. The topic remains an active area of investigation within atmospheric science. Even though jet streams flow high above the surface, their influence is felt at ground level. The timing of frontal passages, the intensity of storms, and the distribution of precipitation are often shaped by upper-level winds. Aircraft pilots are well aware of jet streams. Flights travelling eastward across the Atlantic may shorten travel times by riding strong tailwinds within the jet. Westbound flights often take longer as they face headwinds. The jet stream is not a single continuous river, but rather a shifting band that strengthens, weakens, and meanders with changing atmospheric conditions. It reflects the balance between temperature gradients, Earth's rotation, and pressure differences at high altitude. From the surface, the jet stream is invisible. It leaves no direct mark in the sky. Yet its presence can often be inferred from fast-moving cirrus clouds, or from the rapid progression of storm systems across weather maps. High above daily life, these rivers of air quietly guide the flow of weather across the planet. They link temperature contrasts in one region to storms in another. They steer low-pressure systems borne along fronts. They shape the distribution of warmth and cold. The atmosphere is layered not only vertically but dynamically. What happens at 10 kilometers above the surface influences what happens at sea level. The movement of air at altitude helps determine where rain falls and where skies remain clear. Beneath these high-altitude currents, the oceans continue to store and release vast amounts of heat, interacting with the atmosphere in ways that further shape the patterns overhead. It is easy to think of weather as something that happens only in the air. Clouds gather overhead. Winds sweep across open fields. Rain falls from the sky. But beneath much of that motion lies another vast system, slower, deeper, and in many ways more patient. The ocean covers roughly 70% of Earth's surface. It is not simply a backdrop to atmospheric drama, it is an active participant. Water has a high specific heat capacity. That means it can absorb a large amount of energy before its temperature changes significantly. Compared to land, ocean water warms more slowly during the day and cools more slowly at night. Over the course of a year, this difference becomes even more pronounced. A sandy beach may heat quickly under afternoon sunlight and cool rapidly after sunset. The adjacent ocean changes temperature much more gradually. This difference arises because water molecules can store and distribute energy efficiently through mixing and molecular motion. The energy required to raise the temperature of water is much greater than that required to raise the temperature of dry soil or rock by the same amount. Because of this property, The ocean acts as a massive thermal reservoir. It absorbs vast quantities of solar energy in tropical and subtropical regions. Some of that heat is released back into the atmosphere through evaporation and sensible heat transfer. Some is transported by ocean currents to higher latitudes. This stored heat moderates coastal climates. Regions near large bodies of water often experience smaller seasonal temperature swings than inland areas at similar latitudes. The ocean smooths extremes, but smoothing is not the only role it plays. In certain regions, interactions between ocean and atmosphere produce large-scale climate variability patterns that influence weather across continents. One of the most significant of these is the El Niño Southern Oscillation, often abbreviated as ENSO. ENSO refers to a periodic variation in sea surface temperatures and atmospheric pressure patterns across the equatorial Pacific Ocean. During a normal state, trade winds blow from east to west along the equator, piling warm surface water toward the western Pacific near Indonesia and Australia. This allows colder, nutrient-rich water to upwell near the coast of South America. During an El Niño event, those trade winds weaken. Warm surface water spreads eastward across the central and eastern Pacific. Sea surface temperatures rise above average in those regions. The shift in ocean temperatures alters atmospheric convection patterns. Rainfall that normally occurs over the western Pacific may shift eastward. Regions that are typically dry may experience flooding. Areas accustomed to regular rainfall may face drought. The opposite phase, known as La Niña, occurs when trade winds strengthen beyond normal. Warm water is pushed even farther west. Colder water upwells more vigorously in the eastern Pacific. Atmospheric circulation adjusts accordingly, often producing patterns opposite to those seen during El Niño. The National Oceanic and Atmospheric Administration monitors ENSO conditions through a network of buoys, satellites, and ocean temperature measurements. Changes in equatorial Pacific sea surface temperatures can influence hurricane activity in the Atlantic, monsoon strength in Asia, and winter storm tracks in North America. The ocean does not simply respond to the atmosphere. It interacts with it in feedback loops. Warm sea surface temperatures increase evaporation. Increased evaporation adds water vapor to the atmosphere. More water vapor enhances convection and latent heat release. That release can further alter wind patterns, which in turn affect ocean surface currents and upwelling. The system is dynamic and interconnected. Beyond the surface, ocean circulation operates on longer timescales. Thermohaline circulation refers to the global movement of ocean water, driven by differences in temperature and salinity. The term combines thermo, meaning temperature, and haline, referring to salt content. Cold water is denser than warm water. Saltier water is denser than fresher water. In polar regions, especially in the North Atlantic, surface water cools and becomes saltier as sea ice forms and excludes salt. This dense water sinks and begins a slow journey through the deep ocean. This process helps drive what is sometimes called the global conveyor belt, a system of deep ocean currents that circulate water around the planet over timescales of hundreds to thousands of years. Although thermohaline circulation operates slowly compared to atmospheric winds, it plays a role in distributing heat globally. For example, the Gulf Stream transports warm water from the tropics toward the North Atlantic, contributing to relatively mild winters in parts of Western Europe compared to other regions at similar latitudes. Changes in ocean circulation can influence atmospheric patterns. If sea surface temperatures shift in key regions, pressure systems above them may adjust. Storm tracks may migrate. Rainfall patterns may alter. Ocean and atmosphere exchange energy continuously. Sunlight warms the ocean surface. The ocean releases heat to the atmosphere through evaporation, conduction, and radiation. Winds drive surface currents. Currents redistribute heat. Heat influences pressure patterns. Pressure patterns influence winds. It is a coupled system. Even short-term weather events are influenced by ocean conditions. A tropical cyclone intensifies over warm water because evaporation feeds latent heat into the storm. If the storm moves over cooler water, its intensity often decreases. The temperature of the upper few tens of meters of ocean water can determine whether a cyclone strengthens rapidly or weakens. Similarly, prolonged heat waves over continents may be influenced by persistent ocean temperature anomalies that affect atmospheric circulation patterns. The ocean does not change as quickly as the atmosphere. Its heat content evolves over weeks, months, and years. This slower pace gives it a memory of sorts. Conditions in the ocean today can influence atmospheric behavior months later. Weather, then, is not confined to the sky. It is shaped by what lies beneath. Waves rolling across the surface may appear gentle and rhythmic, but below them, vast volumes of water are storing energy gathered from sunlight. That stored energy influences evaporation rates, humidity levels, and the development of storms. The boundary between ocean and atmosphere is not a dividing line. It is a zone of exchange. Heat, moisture, and a momentum move across it constantly. Understanding weather requires looking downward as well as upward. The sky responds to the sea responds to the sky. Together they form a coupled system that operates across scales from local sea breezes to global oscillations. Within this interplay lies a distinction between short-term atmospheric variability and longer-term patterns that define regional expectations. That distinction clarifies how daily weather relates to broader averages observed over decades. A cold morning, a sudden downpour, a week of bright sunshine. These are experiences of weather. They are immediate, local, and often fleeting. Weather describes the short-term state of the atmosphere at a particular place and time. It includes temperature, wind speed and direction, humidity, cloud cover, precipitation, and atmospheric pressure. Weather changes constantly. A passing front can shift conditions within hours. A developing thunderstorm can alter the sky in minutes. Even on calm days, subtle variations unfold from sunrise to sunset. Climate is something different. Climate refers to the long-term statistical description of weather patterns in a given region. It is not about a single hot day or one snowy afternoon. It is about averages, variability, and trends calculated over decades. By convention, climatologists often use a period of 30 years to define climate normals. This time frame smooths out short-term fluctuations and reveals typical conditions. If weather is what happens today, climate is what tends to happen over many years. For example, a city may have a climate characterized by mild winters and warm summers. That does not mean every winter day is mild or every summer day is warm. It means that when temperatures are averaged across decades, that pattern emerges. Individual weather events can deviate significantly from the average without altering the underlying climate classification. The scientific discipline devoted to studying long-term atmospheric patterns is called climatology. Climatology examines temperature records, precipitation data, atmospheric circulation trends, and interactions between the atmosphere, oceans, land, and ice. It seeks to understand both natural variability and longer-term changes in Earth's energy balance. Institutions such as the Intergovernmental Panel on Climate Change assess scientific research on climate trends. The panel does not conduct original experiments itself. Instead, it evaluates and synthesizes findings from thousands of studies worldwide. drawing on contributions from meteorologists, oceanographers, physicists, and other specialists. Understanding the distinction between variability and trend is central to clarifying the relationship between weather and climate. Variability refers to natural fluctuations that occur over days, months, or even years. A strong El Niño event may produce an unusually warm winter in one region and heavy rainfall in another. A volcanic eruption may temporarily cool global temperatures by injecting reflective particles into the stratosphere. These are examples of variability within the climate system. A trend, by contrast, describes a persistent change in average conditions over extended periods. When global average temperatures rise steadily over decades, that pattern reflects a long-term trend rather than short-term variability. Confusion sometimes arises when short-term weather events are interpreted as evidence for or against long-term climate patterns. A single cold winter does not disprove a warming trend. A single heat wave does not define climate by itself. Climate emerges from the aggregation of countless weather events over time. One way to think about the relationship is to imagine a rolling landscape. Weather represents the individual waves on the surface. Climate defines the shape of the landscape itself. The waves can rise and fall rapidly, but the underlying terrain changes more gradually. Climate sets the boundaries within which weather operates. In a polar climate, even the warmer summer days remain relatively cool compared to tropical regions. In a desert climate, rainfall is infrequent, even though occasional storms may occur. The average state of the system constrains the range of daily possibilities. Temperature gradients between equator and pole, ocean heat distribution, atmospheric composition, and planetary albedo all contribute to defining climate. These factors shape large-scale circulation patterns, such as the Hadley cells and jet streams. Those circulation patterns, in turn, influence daily weather. Climatology also examines feedback mechanisms that operate over longer timescales. Changes in sea ice cover can alter albedo, influencing how much solar radiation is absorbed. Shifts in vegetation can modify surface reflectivity and moisture exchange. Variations in greenhouse gas concentrations can affect the balance between incoming solar radiation and outgoing infrared radiation. The climate system integrates processes occurring in the atmosphere, ocean, cryosphere, and biosphere. Weather forecasting focuses on predicting specific atmospheric conditions over days or weeks. Climate science seeks to understand average behavior over decades and beyond. Both rely on the same physical laws of thermodynamics and fluid dynamics, but they address different questions. The atmosphere may behave unpredictably on short timescales due to its chaotic nature. Edward Lorenz demonstrated in the 1960s that small differences in initial conditions can lead to diverging outcomes in weather simulations. This sensitivity limits precise forecasts beyond a certain time horizon. Yet even within this chaos, long-term statistical patterns remain meaningful. While it may be impossible to predict the exact weather on a specific date years in advance, it is possible to estimate average conditions for a season based on climate models and historical data. The difference between weather and climate is not merely semantic. It clarifies how the atmosphere behaves across timescales. Weather is immediate expression. Climate is accumulated pattern. When daily forecasts mention that conditions are warmer than average, they're comparing short-term weather to long-term climate normals. When climatologists analyze decades of temperature data, they're examining whether those normals are shifting. Both perspectives are necessary. Without understanding weather, climate would be an abstraction. Without understanding climate, weather would seem disconnected from broader context. The atmosphere operates continuously. individual storms rise and dissipate, fronts advance and retreat. Meanwhile, averages are calculated quietly in the background, revealing patterns that extend beyond any single event. Distinguishing clearly between weather and climate prevents confusion and allows the next question to come into focus. How far ahead can the atmospheric behavior be anticipated, and what limits exist on that anticipation? On some mornings, the forecast feels remarkably accurate. The rain arrives within minutes of the predicted hour. The temperature matches expectations. At other times, clouds linger when sunshine was promised, or a storm intensifies beyond what seemed likely. The atmosphere follows physical laws with precision, yet long-term certainty remains elusive. The reason lies in chaos. In the early 1960s, a meteorologist named Edward Lorenz was working at the Massachusetts Institute of Technology on simplified mathematical models of atmospheric convection. His goal was to simulate weather patterns using a set of equations describing fluid motion and heat transfer. During one experiment, he reran a simulation using initial values rounded slightly differently from the original inputs. He expected nearly identical results. Instead, the outcomes diverged dramatically over time. Lorenz discovered what is now known as sensitive dependence on initial conditions. In certain nonlinear systems, very small differences at the beginning can lead to large differences later. The atmosphere is one of those systems. Sensitive dependence does not mean the atmosphere is random. It means that small uncertainties in measurements can grow as time progresses. If two nearly identical atmospheric states are allowed to evolve according to the same physical laws, their trajectories may separate over days or weeks. Lorenz illustrated this concept with a poetic metaphor. He asked whether the flap of a butterfly's wings in Brazil could set off a tornado in Texas. The phrase butterfly effect emerged from this idea. The point was not that butterflies routinely create storms, but that tiny perturbations can, in principle, influence large-scale outcomes in a chaotic system. Weather prediction depends on knowing the current state of the atmosphere as accurately as possible. Meteorologists gather data from weather stations, ocean buoys, radar systems, satellites, and weather balloons. These observations provide temperature, pressure, humidity, and wind information at thousands of locations. Even with this extensive network, measurements are not perfect. The atmosphere is vast. Data coverage is denser over populated regions and sparser over remote oceans or polar areas. Instruments have margins of error. Conditions change between observation times. When forecasting begins, scientists input these measurements into numerical weather prediction models. These models are based on the fundamental equations of fluid dynamics and thermodynamics. They describe how pressure, temperature, wind, and moisture evolve over time. At their core are the Navier-Stokes equations, which govern fluid motion, along with equations for energy conservation and mass continuity. While these equations can be written in compact mathematical form, solving them for the entire globe requires immense computational power. The atmosphere must be divided into a three-dimensional grid, with calculations performed at each grid point. The finer the grid, the more detailed the forecast can be. However, finer grids require exponentially more computing resources. Institutions such as the European Centre for Medium-Range Weather Forecasts operate some of the most powerful supercomputers dedicated to atmospheric modelling. These machines perform trillions of calculations per second, integrating equations forward in time to simulate future states of the atmosphere. Even with these resources, uncertainty grows with time. To address this, meteorologists use ensemble forecasting. Instead of running a single simulation, They run many simulations with slightly different initial conditions. Each run produces a potential future scenario. By comparing the range of outcomes, forecasters can estimate probabilities. If most ensemble members predict rain on a given day, confidence is high. If predictions diverge widely, uncertainty increases. The atmosphere's chaotic nature imposes a practical limit on deterministic forecasts. Beyond roughly 1 to 2 weeks, small errors in initial conditions typically amplify, to the point where precise daily forecasts lose reliability. This limit is not due to a lack of understanding of physics. It is inherent to the system's sensitivity. The growth of error can be understood conceptually. Imagine 2 air parcels with nearly identical temperature and position. Over time, slight differences in their paths may lead one to encounter a rising motion while the other remains stable. That divergence affects cloud formation, pressure patterns, and wind fields. These changes propagate, influencing surrounding regions. The system does not forget its initial state instantly, but it gradually loses detailed memory as small discrepancies expand. Despite this, forecasts have improved significantly over the past decades. Advances in satellite observation, data assimilation techniques, and computing power have extended reliable prediction ranges. What once could be forecast accurately for only 2 or 3 days can now often be predicted a week or more in advance. Data assimilation is a critical process in modern forecasting. It involves combining observational data with model output to produce the best possible estimate of the current atmospheric state. Observations are weighted according to their reliability and integrated into the model's framework. Supercomputing centers continue to refine model resolution and physical parameterizations. They represent processes such as cloud formation, radiation transfer, and turbulence with increasing sophistication. Yet even as models improve, the underlying constraint remains. Weather prediction is not limited because the atmosphere is mysterious. It is limited because it is nonlinear and sensitive. There is a distinction between deterministic predictability and statistical predictability. While predicting the exact state of the atmosphere weeks in advance may be impossible, predicting general tendencies, such as seasonal temperature anomalies associated with El Niño, is more feasible because those patterns involve slower evolving components of the climate system. Short-term weather, especially involving convection and storms, remains more sensitive to initial uncertainties. This interplay between precision and unpredictability gives forecasting its character. Meteorology is both deeply mathematical and inherently probabilistic. The atmosphere evolves according to physical laws that are well established. Pressure gradients accelerate air. Latent heat release fuels convection. Rotation shapes circulation. None of these principles are uncertain. What remains uncertain is the exact path the system will follow when influenced by countless small variations. Understanding this does not diminish forecasting. It clarifies its boundaries. It explains why forecasts improve steadily but never reach perfect certainty. It also reveals why modern forecasting tools rely on probability and ensembles rather than single definitive predictions. Within those tools lies the practical art of translating complex numerical simulations into daily guidance for millions of people. Every weather forecast begins with a question that sounds simple, but is anything but. What is happening in the atmosphere right now? Before computers can project the future, they must understand the present. That understanding comes from observation. Across the world, thousands of surface weather stations measure temperature, atmospheric pressure, wind speed, wind direction, and humidity. Some are automated instruments placed in remote regions. Others are located at airports, where accurate data are essential for aviation safety. These stations provide continuous streams of information, forming the foundation of forecasting. But weather is three-dimensional. Conditions at ground level tell only part of the story. To sample the atmosphere vertically, meteorologists use radiosondes. A radiosonde is a small instrument package attached to a weather balloon filled with helium or hydrogen. Twice daily in hundreds of locations worldwide, balloons are released and rise through the troposphere and often into the lower stratosphere. As they ascend, radiosondes transmit measurements of temperature, pressure, humidity, and wind back to ground stations. These vertical profiles reveal how temperature changes with height, where inversions exist, how moist the air is aloft, and how winds vary with altitude. Such information is crucial for identifying instability, wind shear, and potential storm development. Above these direct measurements, satellites orbit Earth, providing global coverage that ground stations cannot match. Meteorological satellites observe cloud patterns, sea surface temperatures, atmospheric water vapor, and radiation levels. Some operate in geostationary orbit, remaining fixed relative to one region of Earth, offering continuous monitoring. Others travel in polar orbits, scanning the entire globe over time. Infrared sensors on satellites estimate cloud top temperatures, which help determine cloud height. Visible imagery shows cloud structure during daylight hours. Microwave sensors measure moisture content and precipitation intensity through cloud layers. Doppler radar adds another dimension. Radar systems emit pulses of microwave energy that reflect off precipitation particles in the atmosphere. By measuring the time it takes for the signal to return, meteorologists determine the location and intensity of rain or snow. The Doppler capability allows radar to measure the velocity of particles moving toward or away from the instrument, revealing wind patterns within storms. This ability to detect rotation within thunderstorms has greatly improved tornado warning capabilities. All of this data flows into forecasting centers around the world. The World Meteorological Organization coordinates international exchange of meteorological data, ensuring that observations from one country can support forecasts in another. Weather systems do not respect political boundaries, and neither can forecasting. Once observations are gathered, they are fed into numerical weather prediction models through a process known as data assimilation. Data assimilation combines observations with a previous model forecast to create the best possible estimate of the current atmospheric state, often referred to as the analysis. From this starting point, the model equations are integrated forward in time. Because of the chaotic nature of the atmosphere, forecasters do not rely on a single model run. Instead, they use ensemble forecasting methods. An ensemble consists of many model simulations, each starting from slightly different initial conditions or using slightly varied model parameters. These small differences reflect uncertainties in measurement and representation of physical processes. As the ensemble members evolve, they may diverge from one another. The spread of outcomes provides information about forecast confidence. If nearly all ensemble members predict heavy rainfall over a region, the probability of that outcome is high. If half predict rain and half predict dry conditions, uncertainty is greater. Probabilistic forecasting translates ensemble output into meaningful guidance. Instead of stating that it will rain at a specific time with certainty, forecasts may indicate a 60% chance of precipitation. This percentage reflects the proportion of ensemble members producing measurable rainfall over a defined area and time period. Probability does not imply indecision, it quantifies uncertainty. Modern forecasts also include products such as spaghetti plots for hurricane tracks, where multiple projected paths are displayed together. The clustering of lines indicates confidence, while wide divergence signals greater uncertainty. Despite remarkable technological progress, forecasts remain imperfect. Observational coverage, while extensive, is not complete. The oceans still have fewer direct measurements than land areas. Remote polar regions present challenges. Models approximate complex processes such as cloud microphysics and turbulence using parameterizations, which simplify small-scale phenomena into manageable equations. Computing power, though immense, remains finite. Increasing model resolution requires exponentially greater computational resources. Forecasters must balance detail with practicality. Moreover, sensitive dependence on initial conditions ensures that small observational errors can grow over time. Even so, accuracy has improved significantly over the past several decades. A 5-day forecast today often rivals the accuracy of a 2 or 3-day forecast from the late 20th century. Satellite advancements, improved data assimilation techniques, and more powerful supercomputers have extended reliable prediction windows. Forecasting is not about eliminating uncertainty entirely. It is about narrowing it as much as possible and communicating remaining uncertainty clearly. When checking a forecast on a phone or hearing one on the radio, the information presented represents the culmination of millions of observations, complex mathematical calculations, and collaborative international coordination. Behind a simple icon of a cloud or sun lies an intricate system of physics, computation, and global cooperation. Forecasting connects atmospheric science to daily life. It informs decisions about travel, agriculture, emergency planning, and recreation. It helps communities prepare for potential hazards while acknowledging the inherent limits imposed by chaos. The sky may never be predictable with perfect precision, yet each improvement in observation and modelling sharpens understanding. And when conditions intensify into severe or unusual events, the same forecasting systems are tested under the greatest strain, where accurate timing and probability assessments can matter most. Most days the atmosphere expresses itself gently. A breeze drifts across open fields. Rain falls steadily. Clouds gather and disperse without urgency. Yet the same physical system that produces calm afternoons is also capable of extremes. Extreme weather is not a separate set of rules. It is the atmosphere operating near the edges of its energetic range. Consider tornadoes. A tornado is a rapidly rotating column of air that extends from a thunderstorm cloud to the ground. Most form within a specific type of thunderstorm known as a supercell. Supercells develop when strong instability combines with significant vertical wind shear. Wind shear, the change in wind speed or direction with height, allows horizontal tubes of rotating air to form within the lower atmosphere. If a powerful updraft tilts one of these horizontal rotations into the vertical, it can create a rotating updraft called a mesocyclone. Within the mesocyclone, pressure may drop further. As air converges and stretches upward, rotation can intensify through conservation of angular momentum. When that rotating column tightens and extends downward, a tornado may form. Not all supercells produce tornadoes. Precise conditions must align, including sufficient moisture, instability, and shear. Research conducted by the National Weather Service and affiliated laboratories such as the Storm Prediction Center has advanced understanding of these processes. Doppler radar observations reveal rotation within storms before a tornado touches down, improving warning times. Even so, tornado formation remains sensitive to subtle environmental differences. Two storms may look similar on radar, yet only one produces a tornado. Elsewhere, extreme precipitation can take a different form. Atmospheric rivers are long, narrow corridors of concentrated water vapor transported by strong winds in the lower atmosphere. They often originate over tropical or subtropical oceans and extend thousands of kilometers toward mid-latitudes. When these moisture-rich air streams encounter mountain ranges or frontal systems, the vapor condenses and falls as heavy rain or snow. The term atmospheric river reflects their appearance in satellite imagery. They resemble rivers in the sky, carrying vast amounts of water. A single strong atmospheric river can transport more water vapor than the average flow at the mouth of the Amazon River. When such a system stalls or repeatedly impacts the same region, flooding can occur. On the west coast of North America, for example, atmospheric rivers are a major source of winter precipitation. They replenish reservoirs and snowpack, but they can also overwhelm infrastructure during particularly intense events. Extreme temperature events also emerge from circulation patterns. Heat waves develop when high-pressure systems become persistent. Under a strong ridge in the upper atmosphere, air sinks slowly. As it sinks, it compresses and warms. Clear skies allow sunlight to heat the surface further. If the ridge remains stationary for days or weeks, temperatures can rise well above average. The absence of cloud cover reduces evaporative cooling. Soil moisture may decline, amplifying the heat through reduced latent heat flux. The land warms more quickly, reinforcing the high-pressure pattern. These feedbacks can intensify and prolong heat waves. Cold snaps arise when polar air masses move equatorward under amplified troughs in the jet stream. When the jet stream forms deep southward dips, cold Arctic air can surge into regions that normally experience milder conditions. Surface high pressure behind a cold front may allow skies to clear, enabling further radiative cooling at night. Both heat waves and cold snaps illustrate how amplified circulation patterns influence extreme events. Amplification refers to larger than usual waves in the jet stream. When Rossby waves grow in amplitude and slow in movement, they can create blocking patterns. These blocks may trap warm air in one region and cold air in another for extended periods. Extreme weather often arises when multiple factors align. A strong temperature gradient, high moisture content, persistent upper-level support, and favorable wind shear can combine to produce significant events. The atmosphere is not designed to be moderate at all times. It redistributes energy, and sometimes that redistribution is abrupt. The National Weather Service studies these extremes to improve warnings and preparedness. Statistical analyses of past events combined with improved modelling help identify patterns associated with severe outbreaks, major floods, or prolonged heat waves. It is important to recognise that extremes are part of the natural variability of the atmosphere. Records of severe storms, droughts, and cold winters extend back through historical documentation. What changes over time are the baseline conditions within which these extremes occur. A heatwave superimposed on a warmer average climate produces higher absolute temperatures than one occurring in a cooler baseline. Similarly, changes in sea surface temperatures can influence the intensity of heavy rainfall events. Extreme weather demonstrates the full dynamic range of atmospheric behavior. It reveals how energy gradients, moisture availability, and circulation patterns interact at their most intense. A tornado represents concentrated rotational energy within a localized column. An atmospheric river represents a large-scale moisture transport. A heat wave reflects persistent upper-level ridging. A cold snap illustrates rapid displacement of polar air. These events differ in scale and impact, yet they are unified by the same physical principles governing everyday weather. The atmosphere does not switch to a different set of laws during extremes. It follows thermodynamics, fluid dynamics, and conservation principles consistently. What changes is the magnitude and alignment of the driving forces. Understanding extremes requires viewing the atmosphere as an interconnected system, influenced by both short-term disturbances and broader planetary patterns. Beyond individual events, longer-term processes shape the frequency, intensity, and distribution of these extremes across decades and centuries. The atmosphere does not simply respond to change, it often responds to its own response. This layered reaction is known as feedback. A feedback loop occurs when a process within a system influences that same process, either by amplifying it or by reducing it. In atmospheric science, feedbacks help determine whether an initial change remains small or grows larger over time. There are two main types of feedback, positive and negative. A positive feedback amplifies an initial change. If a warming tendency triggers processes that lead to further warming, the loop is considered positive. A negative feedback dampens change. If a warming tendency activates processes that reduce that warming, the loop is negative. Neither term implies good or bad. They describe direction of influence. One of the most important feedbacks in the atmosphere involves water vapor. Water vapor is the most abundant greenhouse gas in Earth's atmosphere. It absorbs and emits infrared radiation, trapping heat that would otherwise escape to space. The amount of water vapor the air can hold increases with temperature. This relationship follows the Clausius-Clapeyron relation, which describes how saturation vapor pressure rises exponentially with temperature. If the atmosphere warms slightly due to an external forcing such as increased greenhouse gas concentrations or increased solar input, it can hold more water vapor. As water vapor increases, additional infrared radiation is absorbed and re-emitted within the atmosphere. This enhances the greenhouse effect, leading to further warming. This is water vapor feedback, and it is considered a positive feedback. The initial warming does not originate from water vapor itself in this scenario. Instead, water vapor amplifies the warming caused by another factor. Climate modeling research consistently identifies water vapor feedback as one of the strongest amplifiers in the climate system. Observational studies using satellite measurements confirm that atmospheric moisture content has generally increased in a warming atmosphere, consistent with thermodynamic expectations. Cloud feedback is more complex. Clouds influence Earth's energy balance in two primary ways. Low, thick clouds reflect incoming solar radiation, increasing planetary albedo and producing a cooling effect. High, thin clouds tend to trap outgoing infrared radiation, contributing to warming. If warming leads to more low reflective clouds, that would represent a negative feedback. If warming leads to more high insulating clouds, that would represent a positive feedback. The difficulty lies in predicting how cloud distribution, altitude, thickness, and coverage will change under different conditions. Cloud microphysics involves processes occurring at scales far smaller than global climate models can directly resolve. Droplet formation, ice crystal growth, and turbulence all influence cloud properties. Modern climate models incorporate cloud parameterizations to represent these processes. Research groups at institutions such as the National Centre for Atmospheric Research and the European Centre for Medium-Range Weather Forecasts continually refine these representations. Despite progress, cloud feedback remains one of the largest sources of uncertainty in climate projections. Some observational evidence suggests that certain low cloud types may decrease slightly with warming in some regions, potentially reinforcing warming. Other studies highlight regional variations that complicate simple conclusions. Feedbacks do not operate in isolation, they interact. Consider sea ice feedback. When temperatures rise in polar regions, sea ice melts. Ice has high albedo and reflects much of the incoming sunlight. Open ocean water is darker and absorbs more solar energy. As ice melts, more ocean surface is exposed, absorbing additional heat and leading to further melting. This is a positive feedback. At the same time, increased evaporation from warmer oceans may lead to more cloud formation in some areas, potentially moderating warming locally. These interacting feedbacks create nonlinear responses. Nonlinear amplification means that the system's response is not directly proportional to the initial forcing. A small change can lead to disproportionately large consequences if reinforcing feedbacks are present. Conversely, strong negative feedbacks can stabilize the system, limiting change. Nonlinearity is a defining feature of atmospheric dynamics. It explains why certain thresholds matter. When surface temperatures cross specific ranges, atmospheric circulation patterns may shift. When moisture reaches particular levels, convection may intensify rapidly. Climate modeling research seeks to capture these nonlinear interactions. Models simulate how radiation, convection, moisture transport, and surface processes interact over time. By running multiple simulations under varying conditions, scientists assess how feedbacks influence long-term outcomes. The Intergovernmental Panel on Climate Change evaluates these modelling studies to assess confidence in projected changes. While uncertainties remain, especially regarding clouds and regional feedbacks, the broad mechanisms of water vapour amplification and ice albedo feedback are well supported. Feedback loops also operate on shorter timescales in weather systems. In a developing thunderstorm, latent heat release reinforces updraft strength, which in turn enhances further condensation. That is a positive feedback at a local scale. Conversely, downdrafts that cut off warm air supply act as a negative feedback, eventually weakening the storm. The atmosphere is therefore a system of interlocking feedbacks, operating across scales from individual clouds to global circulation. Understanding feedbacks clarifies why certain changes persist or intensify. It explains how gradual warming can lead to amplified polar temperature changes. It reveals why moisture content responds predictably to temperature shifts. At the same time, feedbacks remind us that the atmosphere does not move in straight lines. Responses curve and branch. Processes reinforce or counteract one another. The sky above may appear calm, but beneath that calm lies a network of reinforcing and balancing mechanisms, continuously adjusting to maintain energy equilibrium. Within this network, chemistry also plays a role, influencing radiation, temperature structure, and the composition of the air itself. The atmosphere is not only a moving fluid, it is also a reactive chemical mixture. While nitrogen and oxygen dominate its composition, trace gases exert outsized influence on temperature, structure, and radiation balance. Chemistry, though often invisible, shapes how energy is absorbed, emitted, and redistributed. High above the troposphere, in the stratosphere, lies a region where temperature behaves differently. Instead of decreasing with altitude, it increases. The reason is ozone. The ozone layer is a concentration of ozone molecules found primarily between roughly 15 and 35 kilometers above Earth's surface. Ozone is a molecule composed of 3 oxygen atoms. It forms when ultraviolet radiation from the sun splits an ordinary oxygen molecule, which contains 2 oxygen atoms, into separate atoms. These free oxygen atoms can then combine with other oxygen molecules to form ozone. This sequence of reactions is an example of photochemistry, which refers to chemical reactions driven by light. In this case, high-energy ultraviolet radiation initiates the process. ozone absorbs a significant portion of incoming ultraviolet radiation, particularly ultraviolet B and ultraviolet C wavelengths. When ozone molecules absorb this radiation, they convert light energy into heat. This absorption warms the surrounding air, creating the temperature inversion characteristic of the stratosphere. Without ozone, ultraviolet radiation would reach the surface in much greater intensity, posing severe biological risks. The ozone layer acts as a protective shield. In the late 20th century, scientists observed a significant depletion of stratospheric ozone over Antarctica during the southern hemisphere spring. Research led by atmospheric chemists such as Mario Molina and F. Sherwood Rowland identified chlorofluorocarbons, or CFCs, as the primary cause. These synthetic compounds, once widely used in refrigeration and aerosol sprays, release chlorine atoms when broken down by ultraviolet radiation in the stratosphere. A single chlorine atom can catalytically destroy thousands of ozone molecules through repeated chemical cycles. These reactions were particularly effective in the cold polar stratosphere, where unique cloud formations known as polar stratospheric clouds facilitated chlorine activation. In response to this scientific evidence, the Montreal Protocol was adopted in 1987. This international agreement committed nations to phasing out the production and consumption of ozone-depleting substances. The protocol is widely regarded as one of the most successful environmental treaties. Observations indicate that stratospheric ozone levels are gradually recovering, though full restoration is expected to take decades. The ozone example demonstrates how atmospheric chemistry directly influences temperature structure and radiation balance. Lower in the atmosphere, greenhouse gases play a different but equally significant role. Greenhouse gases include carbon dioxide, methane, nitrous oxide, water vapor, and ozone in the troposphere. These gases absorb infrared radiation emitted by Earth's surface. After absorbing this energy, they remit it in all directions, including back toward the surface. This process reduces the rate at which heat escapes to space, maintaining a warmer surface temperature than would otherwise exist. The greenhouse effect is a natural and essential component of Earth's climate system. Without it, average surface temperatures would be far colder and liquid water would be scarce. Carbon dioxide is present at a concentration of a few hundred parts per million, yet it exerts significant influence because of its ability to absorb infrared radiation at specific wavelengths. Methane, though less abundant, is even more effective per molecule at trapping heat over shorter timescales. The interaction between greenhouse gases and radiation determines the vertical temperature profile of the atmosphere. In the troposphere, greenhouse gases contribute to warming from below. In the stratosphere, increased greenhouse gas concentrations can lead to cooling, because less infrared radiation reaches those altitudes from below. This contrast illustrates how chemistry and radiation interplay across layers. Photochemical reactions also occur in the troposphere. Urban air pollution can lead to the formation of ground-level ozone through reactions involving nitrogen oxides and volatile organic compounds in the presence of sunlight. Unlike stratospheric ozone, which protects life, tropospheric ozone can harm respiratory health and vegetation. Atmospheric chemistry is therefore not confined to a single layer. It operates throughout the vertical structure of the atmosphere, influenced by sunlight, temperature, and human activity. Climate models incorporate detailed chemical processes to simulate how gases interact with radiation and with each other. These models account for photochemical reactions, emission sources, atmospheric transport, and removal mechanisms such as deposition or chemical breakdown. Chemistry shapes not only temperature but also cloud formation. Aerosol particles, some produced by natural sources and others by industrial activity, act as condensation nuclei. Changes in aerosol concentrations can influence cloud droplet size and reflectivity, thereby affecting albedo. The sky is not chemically static, it is dynamic and reactive. Ultraviolet radiation drives reactions that build and break apart ozone. Infrared radiation interacts with greenhouse gases to regulate temperature. Human-produced compounds can alter these balances, as demonstrated by the history of CFCs. Physical motion and chemical composition are intertwined. Rising air transports chemical species upward. Stratospheric circulation redistributes ozone. Surface emissions are carried by winds across continents and oceans. Understanding weather fully requires acknowledging this chemical dimension. Pressure gradients move air. Temperature gradients drive convection. But chemical composition determines how radiation is absorbed and emitted, influencing those temperature gradients in the first place. The atmosphere is at once a fluid and reactor, governed by thermodynamics and photochemistry together. From nuclear fusion in the sun to ozone formation in the stratosphere, from evaporation over oceans to infrared absorption by greenhouse gases, energy and matter interact continuously. The moving air, the shifting clouds, and the rotating storms all unfold within this chemically active environment, where even trace components help define the structure of the sky. When stepping back from individual storms, fronts, or cloud formations, a larger pattern begins to appear. The atmosphere is not a collection of isolated parts, it is a system. In environmental science, systems theory provides a framework for understanding how interconnected components interact to produce collective behavior. A system consists of elements linked by relationships, exchanging energy and matter. The atmosphere fits this definition precisely. It exchanges heat with the surface, moisture with the oceans, momentum with Earth's rotation, and radiation with space. Within this system, no single process operates independently. Convection interacts with radiation. Chemistry alters temperature gradients. Ocean currents influence pressure fields. Each component affects others in continuous feedback loops. One of the central ideas in systems theory is emergent behavior. Emergence occurs when complex patterns arise from simple interactions among smaller elements. No individual air molecule intends to create a hurricane. No single droplet plans to organize into a cloud band. Yet through countless local interactions governed by physical laws, large-scale structures form. A hurricane, for example, emerges from interactions between warm ocean water, rising moist air, pressure gradients, and planetary rotation. Each step follows thermodynamics and fluid dynamics. Together, they generate a rotating system spanning hundreds of kilometers. Similarly, global circulation cells emerge from uneven solar heating and Earth's rotation. Individual parcels of air respond locally to temperature differences and pressure gradients. Collectively, they produce Hadley cells, feral cells, and polar cells that span hemispheres. This scaling from local to global is fundamental. At a small scale, a rising bubble of warm air cools and condenses, forming a cloud. At a larger scale, thousands of such updrafts combine to influence regional pressure patterns. At planetary scale, energy imbalances between equator and pole drive circulation belts and jet streams. The atmosphere operates across a vast range of spatial and temporal scales. Turbulence at the scale of meters influences cloud microphysics. Synoptic systems spanning thousands of kilometers shape continental weather. Climate oscillations unfold over years to decades. Interdisciplinary atmospheric research draws on physics, chemistry, mathematics, oceanography, and computer science to understand these interactions. Institutions such as the National Centre for Atmospheric Research, the European Centre for Medium-Range Weather Forecasts, and university research groups around the world collaborate to study coupled models that integrate atmospheric dynamics with ocean circulation, land processes, and chemical cycles. These models treat the atmosphere as a complex adaptive system. They incorporate equations describing momentum, heat transfer, moisture transport, radiation balance, and chemical reactions. They simulate how perturbations in one component ripple through others. Balance is a recurring theme. The atmosphere is constantly seeking equilibrium in response to energy imbalances, yet it rarely achieves static balance. Instead, it maintains a dynamic equilibrium, adjusting continuously. Warm air rises and cools. Cold air sinks and warms. Moisture evaporates and condenses. Radiation enters and leaves. Order arises within this motion. Jet streams form consistent pathways. Circulation cells maintain recognizable structures. Seasonal patterns repeat with regularity. Despite chaos at small scales, large-scale organization persists. This coexistence of order and chaos defines the atmosphere's character. Chaos theory explains sensitive dependence on initial conditions. Systems theory explains how organized structures can still emerge within that sensitivity. Consider a snowflake forming within a cloud. Each crystal grows according to molecular interactions between water vapor and ice surfaces. Temperature and humidity determine branching patterns. The result is intricate symmetry, emerging from microscopic processes. On a vastly larger scale, planetary wave patterns curve through the jet stream. Those waves emerge from conservation of angular momentum and temperature gradients. The same principles operate at different scales. Self-organization does not imply conscious coordination. It describes spontaneous pattern formation, resulting from internal interactions. In the atmosphere, energy flows drive these interactions. Solar radiation provides input. Infrared emission to space provides output. Between these flows, motion and chemistry rearrange energy spatially and temporally. Feedback loops contribute to this organization. Positive feedback can amplify developing systems such as strengthening convection within a tropical cyclone. Negative feedback can stabilize systems such as radiative cooling, balancing surface heating overnight. The atmosphere therefore behaves neither randomly nor rigidly. It fluctuates within constraints imposed by physical laws and boundary conditions. Even extreme events fit within this framework. A tornado emerges from instability and shear. An atmospheric river forms from concentrated moisture transport along circulation pathways. These phenomena are not anomalies in the system. They are expressions of its dynamic potential. Viewing the atmosphere as a self-organizing system encourages holistic understanding. Instead of isolating wind from moisture or temperature from chemistry, it recognizes interdependence. Energy drives motion. Motion redistributes heat and moisture. Chemistry modifies radiation. Radiation influences temperature gradients. Temperature gradients reshape motion. Round and round the processes flow. On a calm evening, when clouds drift quietly and winds soften, it may seem as though the atmosphere rests. In reality, it continues its adjustments at scales too broad or subtle to notice immediately. From the microscopic clustering of water molecules to the sweeping arc of a jet stream, the sky organizes itself through simple rules applied endlessly across scales. The result is a living tapestry of motion and balance, intricate yet grounded in consistent principles. Understanding this integrated system allows the final pieces to settle into place: the wind, the rain, the storms, the heat waves, the clouds, and the chemical reactions all belong to one continuous story of energy moving through air. After tracing clouds, winds, oceans, chemistry, and circulation patterns, the picture can feel wonderfully complex. There are jet streams curving across hemispheres, microscopic droplets forming around aerosol particles, rotating storms drawing heat from tropical seas, and chemical reactions unfolding in the stratosphere. It is easy to see weather as an endless list of phenomena, yet beneath that variety lies a single unifying idea. Weather is the redistribution of energy through air. The sun delivers energy unevenly across Earth's surface. The equator receives more solar radiation than the poles. Land heats differently from ocean. Dark surfaces absorb more energy than bright ones. These differences create temperature gradients. Temperature gradients create pressure gradients. Pressure gradients create motion. That motion is the atmosphere attempting to reduce imbalance. Thermodynamics provides the foundation. Warm air expands and becomes less dense. Cooler air contracts and becomes denser. The ideal gas law, expressed in words as pressure multiplied by volume, equals the number of gas particles multiplied by the gas constant multiplied by temperature, links temperature, pressure, and density in a precise relationship. When temperature changes, the balance shifts. Air rises or sinks. Convection begins. Rotation shapes that motion. Earth's spin introduces the Coriolis Effect, deflecting moving air and organizing flows into trade winds, westerlies, and polar easterlies. On a larger scale, circulation cells form. The Hadley cells move energy away from the equator. The feral cells and polar cells continue that transport toward higher latitudes. Jet streams carve fast-moving rivers of air through the upper troposphere, steering storms along predictable paths. Water vapor adds amplification. Through evaporation, energy absorbed from sunlight becomes stored as latent heat. Through condensation, that energy is released aloft, fueling updrafts and intensifying storms. A seemingly simple phase change, liquid to vapor and back again, powers towering cumulonimbus clouds and tropical cyclones spanning hundreds of kilometers. At the smallest scale, microscopic condensation nuclei provide surfaces on which droplets form. A speck of sea salt or dust becomes the starting point for a cloud. At the larger scale, planetary waves ripple through the jet stream, guiding weather systems across continents. From micrometers to thousands of kilometers, the same physical laws apply. Fluid dynamics governs how air accelerates in response to forces. Thermodynamics governs how heat is exchanged and transformed. Radiative transfer governs how energy enters and leaves the atmosphere. Chemistry influences which wavelengths of radiation are absorbed and emitted. Systems theory reveals how local interactions produce global patterns. Even extreme events follow this framework. A tornado is a concentrated expression of rotation and instability. An atmospheric river is a focused corridor of moisture transport. A heat wave reflects persistent high pressure and subsiding air. Each is an expression of energy redistribution under specific boundary conditions. Weather is not separate from climate. Climate sets the average state within which weather unfolds. Nor is weather separate from the ocean. The sea stores and releases heat, shaping atmospheric patterns. Nor is weather separate from chemistry. Greenhouse gases and ozone determine how radiation is absorbed, influencing temperature structure. Everything connects. Despite its complexity, the atmosphere does not invent new rules from one day to the next. It follows conservation of energy, conservation of mass, and conservation of momentum. It responds to imbalances by moving toward equilibrium, though equilibrium itself is dynamic rather than static. The sky may appear chaotic at times, but that apparent disorder arises from countless interacting components operating under consistent principles. Sensitive dependence on initial conditions limits precise prediction, yet statistical patterns persist. Circulation cells reappear season after season. Monsoons follow predictable rhythms. Storm tracks shift but remain guided by upper-level winds. Weather is both predictable in structure and unpredictable in detail. A breeze brushing past the face is part of a larger circulation linking equator to pole. A raindrop falling on a rooftop began as water evaporated from an ocean warmed by sunlight minutes, days, or weeks earlier. A cloud forming over a mountain signals air forced upward, cooling according to the adiabatic lapse rate. Seen in this way, weather becomes less mysterious and more coherent. It is the atmosphere performing its continuous task of moving energy from where it is abundant to where it is scarce. It does so through rising and sinking air, through rotating systems, through shifting pressure fields, and through chemical interactions that shape temperature profiles. The scale can be humbling. A single thunderstorm releases energy equivalent to many human power plants operating simultaneously. Yet that energy originated from ordinary sunlight and ordinary water vapor. The simplicity of the underlying laws contrasts with the richness of the patterns they produce. When looking up at the sky, whether it is clear, clouded, or stormy, it is possible to see more than shifting shapes. It is possible to recognize a vast, self-organizing system in motion, balancing forces, redistributing heat, and maintaining the delicate equilibrium that makes life possible. Weather is not a collection of disconnected events. It is a single, ongoing process, unfolding in air that is thin, dynamic, and governed by the quiet consistency of physics. Look up once more at the sky, and let everything settle into a single idea. Weather is the movement of energy through air. It begins with sunlight arriving from a star nearly 150 million kilometers away. That energy does not land evenly. It warms the equator more than the poles. It heats land differently than ocean. It is absorbed, reflected, stored, and re-released. Every difference in temperature that follows is a small imbalance waiting to be resolved. Air responds. Warm air expands, becomes less dense, and rises. Cooler air sinks. Pressure gradients form. Winds begin to move. Rotation curves those winds into sweeping patterns that circle the globe. Moisture evaporates from warm oceans, carrying hidden energy upward. When that vapor condenses, the stored energy returns to the atmosphere, strengthening motion. Clouds appear not as decoration, but as visible markers of invisible thermodynamics. Storms spin not from chaos, but from conservation of momentum and the steady influence of the Coriolis Effect. Jet streams race overhead because temperature contrasts demand adjustment. Oceans store heat patiently, releasing it slowly and shaping patterns across seasons and years. Even chemistry plays its role. Ozone absorbs ultraviolet radiation, warming the stratosphere. Greenhouse gases interact with infrared radiation, influencing how much heat remains near the surface. Every layer, every molecule participates. Nothing operates alone. The sun provides energy. Gravity holds the atmosphere close. Earth's rotation organizes motion. Water amplifies change. Oceans buffer extremes. Chemistry fine-tunes temperature structure. Feedback loops reinforce or moderate responses. From microscopic condensation nuclei to planetary-scale circulation cells, each component contributes to the whole, and through all of it, the same principles apply. Conservation of energy, conservation of mass, conservation of momentum, thermodynamics, fluid dynamics, radiative transfer. Weather may appear unpredictable at times, and indeed precise details shift from hour to hour, but the underlying rules remain constant. The atmosphere is not improvising, it is responding. A breeze drifting across a quiet field is part of global circulation linking equator and pole. A single raindrop began as sunlight warming ocean water. A towering storm is the organized release of stored heat. A winter cold snap reflects the movement of air masses shaped by upper-level waves. When seen in isolation, each event can feel separate. When seen together, they form a continuous process. The sky above is not merely a backdrop, it is an active, self-organizing system, adjusting constantly to balance energy flows. It breathes in sunlight, it exhales infrared radiation, it shifts, circulates, condenses, and clears. There is a quiet elegance in that. Weather is not magic, nor is it mystery beyond understanding. It is complexity emerging from simplicity. It is structure arising from motion. It is imbalance moving toward equilibrium, again and again. The next time clouds gather or wind rises, it can be seen as part of that larger pattern. Energy arriving from the sun is being redistributed. Heat is travelling. Water is cycling. Air is responding to gradients written across the planet. Above, the atmosphere continues its steady work, thin yet powerful, delicate yet dynamic, governed by laws that have operated for billions of years. And within that motion, life persists comfortably beneath a sky that never truly rests, yet rarely loses its balance.